Excellent connection. That's what I like to hear. Looking good. Okay. So, the first thing to ask is, what do you remember about the pumping lemma? We did the pumping lemma on finite automata.
Pumping lemma, yeah.
Yes.
Pumping lemma is like when you visit multiple states.
I have more states than I have letters.
Letters.
Yes.
That's pumping lemma.
And so, or more letters than states. Sorry, backwards. The string is longer than the number of states.
So you can visit more
Yep. And so you
multiple
do
states with it.
And we did the example with 1, 1, 0, 1, 1, where we found we could repeat the 1, 0, 1.
1, 0.
And we can repeat that as many times as we want, and the end of the string will still have 2 1s.
2 1s.
So we will still accept it with our same automata. Okay. It may occur to you that this is going to be much, much more complicated with the context-free grammar, because context-free grammars are much, much more complicated. So here we go. The context-free pumping lemma is, it accomplishes the same goals, which is there exist languages which the specification of them is too complicated to be expressed with a context-free grammar. You require a more powerful way of specifying languages. That more powerful way is the Turing machine, and then there exist languages that cannot be specified with the Turing machine, right? So we need more power. So this is going to be our more powerful pumping lemma, that there is a technique that is more powerful than finite automata, and we're going to show that even that technique is not powerful enough to express all languages, right? We're going to state the lemma, and then we're going to prove the lemma, and then we're going to show a few examples. This is mostly going to be a proof by picture. There's going to be a lot of graphics in this made with TIKZ, which is a LaTeX library. So I'm going to show you a little bit of LaTeX as well. It is still important to me that any idea you have visually, you have some programming way to express it. So that is also going to be incorporation here. Okay, so what do we want to do? Well, the first thing we want to do is we always want to avoid the trap of saying, I thought about it really hard, and I couldn't solve the problem, so that means it's impossible, right? So what we cannot say is, I thought about it really hard, I could find no PDA that recognizes this language. And you know, I'm pretty smart and pretty hardworking, so I think if there were one, then I would have found it. I don't believe you, because I've seen some absolutely astounding things that I would not have thought of could have been recognized by a PDA, and vice versa, right? I've seen errors in proofs, and I've made errors in proofs where I was sure that language could be recognized by a PDA, and I even thought it was easy. And I just made one little tiny mistake, and I couldn't perceive it, right? So it's important to always write proofs. And in my case, I'm specifically writing proofs that other people have also written, so I know that the outcome is correct, right? I check and I say, ah, yes, my proof looks a lot like this proof by someone else who's gotten it passed through academic peer review, right? Unless you're planning on pursuing a doctorate in computer science or computational math or something, right? You don't ever have to worry about your proofs being correct. Really, what you want to do is be able to understand them well enough to be better at your job, right? So that's the usefulness of this. Okay, so it is not sufficient for us, for mere mortals like us, we often say, to say, I couldn't find the language, so it must not exist. We have to do something else. And the other thing we're going to do is the pumping lemma. I'm going to persuade you that this is hard to do. We're going to take a sigma, and this is going to be ternary, 3 characters, 0, 1, 2. And we're going to say we're going to take some language B, which is k0s, followed by k1s, followed by k2s. We have demonstrated that we can find this first 2/3 with a grammar using the equivalents in the stack. Yes, right. We push a bunch of zeros on the stack, we pop them off. If at the end of our string we have nothing left on the stack, then that means we have the same number of zeros and ones and we accept it, right? And then I know what you're thinking. You're thinking, well, why don't I just do that with 2s? Ha, good luck, because you just used up all of the stack. You have no idea how big k is now, right? And you don't really have a way to manipulate the stack to keep track of k twice. That's a bit silly, right? So how are you going to accept that? And, well, it turns out it's not a context-free language. And not a context-free language means 2 things. It means there exists no push-down automata that recognizes that language. There is no function that can be written that can be programmed into a push-down automata, such that push-down automatas only accept strings of this form. Cannot be done. Separately, there is no context-free grammar that produces all of the strings of this language. You essentially need some context to know that you're adding the same number of 2's or 0's, is what this kind of breaks down to. So this grammar, or this language, is not a context-free language. There is no PDA, there is no CFG. We just don't have any real way to deal with these 2's, but we shouldn't trust ourselves. There might be some really clever way. What if, for example, every time we read a 0, we push both a 0 and a 1 onto the stack, and then we read off all of the 1's and we match them with either a 1 or a 0, or perhaps we push the 1's back onto the stack, something like that. We should be tempted to conclude maybe there's some special stack character we can put in between the middle of it or something like that, right? You kind of want to think, oh, every time I read a 0, I push 2 0's onto the stack, and when I'm halfway through the 0's, I push a special stack character on the stack. Well, you can't do that because you don't know when you're halfway through the 0's, right? So there's all of these things that we can't quite do. So we're going to do the pumping lemma, and we're going to prove it. This is the, what I call regular pumping lemma. And I don't mean like normal or typical. Regular here is meant to mean regular language. So when we say regular pumping lemma, we're referring to the fact that it describes regular expressions, regular languages, or finite automata. We've seen this before, and just to reiterate, we essentially have some substring in the middle of our string that goes in between the repeated states, and we can have as many occurrences or as few occurrences, including 0, of that string as we would like, right? And we have the additional restriction that y is of non-zero length, and that the prefix, which contains x and y, is fewer than the number of states, right? And it only has to be fewer by a little bit, so that's very easy to do. Okay. There's a natural reason to assume that happens, right? So you're necessarily repeating a state once, and you're necessarily going to an accepting state at some point. So you know that anything that has any repeats in it at all is definitely going to be of longer than that before you get back to your loop. Okay. So we say xz, xyz, xyz are all elements of A being the language, which we are referring to. And we call this language, that is uppercase A, to represent it as a set of lowercase a's. And it is, in fact, a special kind of set, which is an ordered set, so it's a sequence, or an ordered collection. And we call it A instead of M or R or something like that, because it's not necessarily the case that A corresponds to a regular language, and it's not necessarily the case that that corresponds to a finite automata. It so happens to do that, but this is true of any regular language, regardless of whether it's specified by an automata or by a regular expression. So we're going to pump up the number of occurrences of y, and we can do that exact same thing, this notion of pumping up the occurrences of a substring, and we can do it with a context-free grammar. But we're going to do it with considerably more sophistication. And the additional sophistication is essentially going to create a sandwich. On the outside of the sandwich, we're going to have u and z. Those are the prefixes and the postfixes. The prefixes are going to convey us to some internal string, very similar to y, and the suffix is going to convey us to some accepting state at the end. So we're not going to talk too much about u and z other than that they exist. What we really care is there's some part in the internals of the context-free grammar where the repeats will take place. The repeats take place in v, x, y. And I want to point out here I skipped w. And I skipped w because we've already used w in these lectures to refer to words. So I'm just trying to avoid double using that. So that's why we have u, v, x, y, z. There's not a magical reason to choose that. We're just trying to be clear. Okay, so we have a context-free language. We also term it A for the same reason we term the other one A. We have some P, which is a natural number, and that natural number, we're going to compare it to our number of states. Or in the case of a context-free grammar, we're going to compare it to our number of substitutions or rules, right? Okay, so then we have some S, which is this string of 5 parts. The string in total is longer than RP, which is some large number, and we will decide what the large number it is later. And what this means is the internals are a little bit sophisticated, right? But I essentially have prefix, beginning of the middle, end of the middle, and suffix. Perhaps, I don't know if you're into burgers or something like that, but you have the bun, the cheese, the burger, the lettuce, and then the closing bun. Something like that is a way to imagine this, right? I had a very good burger on Thursday. That's why I've been thinking about them. And so what you can do on your burger is it can still be a single burger if it has twice as much cheese and twice as much lettuce on it. And we still refer to it as a burger if you take off the cheese and lettuce. So what we're going to do is we're going to allow our customers to determine the amount of cheese and lettuce they want to have on their burger, right? We're going to have a few restrictions. We do not require the burger to have both cheese and lettuce, but it must have one. So V and Y, which are the things in between the bun and the patty, one of those must exist. It does not have to exist on both sides, but we also cannot conclude which side it would exist on, right? And so what we're going to require, and this has to be greater than 0 because this is the thing we're going to pump up, right? So I can order a single patty burger of arbitrary size by adding 400 leaves of lettuce to it. That's allowed, right? And then the intermediate part, the lettuce, the patty, and the cheese, or whatever, all of that is going to be of length less than p. So we're going to have the repeat in there, and there's going to be fewer of that stuff than there is number of total states. So that's what we're all going to put together. We can envision perhaps the total states of the stations in the kitchen at the McDonald's that is assembling our burger, or something of this nature. Okay, so we have our context-free pumping Leno. And this is how it works. U, X, Z is an element of the alphabet. We remove V and Y. We are allowed to have in V and Y, and we are allowed to have repeats of V and Y. One thing I do want to point out is we always have the same number of repeats in V and Y, and that is going to become quite important later. So how does this work? We're going to pump up occurrences of V and Y at the same time. Both of them are going to increase.
Why can't we have 2 X's?
Why can't we have 2 X's? No particular reason. So that would just be unhelpful for this proof with the way it's defined, right? The thing we want is we want there to be some string in the middle and strings on the outside, and we want to be able to inflate in between them. The reason we want to be able to inflate in between those two things is because the shape of the context-free grammars. Context-free grammars can add terminals before a variable, and they can add terminals after a variable. So we're always going to be expanding on one side of the variable. This V and this Y essentially correspond to things that are added on one side of a variable more than once, because we're going to follow a substitution rule more than once. So it is possible, of course, to repeat something in the middle of the string, but we don't really accomplish our goals doing that, which is we don't demonstrate we can't have a context-free language. So that's why we don't repeat X. You can always sort of slice up a string and give it aliases however you like. That's always, you have that power, right? The reason we do this is because it accomplishes our goals. So here's the sketch of the proof. We're going to imagine an arbitrarily long string, and I always say imagine a string of length 1 million. I'm thinking of 1 million zeros, right? Okay. We'll be precise later, and we'll get back to this. Perhaps I imagine 300,000 zeros a 1, 300,000 zeros another 1, and then another 300,000 zeros. And so my V and my Y will both be the 1, and I can increase it an arbitrary number of times. Recall the parse trees, and that's that thing where we say we have E, and we have E plus T, and then we have T plus T, and then we have F plus T, and then we have A plus T, and then T becomes T cross F or something like that. I don't remember. So we have a parse tree. The parse tree is very high. This is what one of them looks like, right? This is the simplified one, where we only have E, right? And so this is A plus E cross E. So this isn't even finished yet. We're still going to have to perform some substitutions here. But this thing is only going to be 5 long, and it is already minimally 2 high, minimally 3 high, because we have to substitute these E's. So for a string of length 5, we have a parse tree, or a derivation, of length 3. So if I have a string of length 1 million, I expect the parse tree to be quite high, and we don't know how high, but perhaps we'll say 100,000. Perhaps in general we add fewer than 10 characters per substitution, right? All of our substitutions so far have added at most 2 characters, and many of them have added 0, right? So let's check in. Can we create a string of length 1 million by way of a parse tree of height 1? say I want to create the string 1 million zeros. Can I create that in a single substitution?
Million zeros
Mm-hmm.
in one substitution.
Yeah.
I think we can do it, right?
I think we can too. So you can, right? You can say the starting variable is substituted for 0 to the power of 10 to the power of 6, which is exactly 1 million zeros. What makes this thing work is not actually that we can't add 1 million zeros at a time. It's that if this is your substitution rule, there's no way to get 1,000,001 zeros. And so it doesn't actually help you. What this just means is this means that whatever I'm pumping is also going to be a size of 1 million, because all of my blocks are of size 1 million. So when we say very long, the string is very long relative to how big the rules are. It's not very long compared to like how long a book is. It's a length that is relevant to the context-free grammar in particular, right? So if I have a context-free grammar that's passing around strings of length 1 million, no problem. I'll just multiply my pumping distance by 1 million, and I'm allowed to do that because it's any finite number. I can multiply it by 1 billion if I have to, right? I can always have 1 million times more length than I need. So this was the first obvious problem I thought of. I was like, what if I just have a substitution that produces very, very large strings very quickly? No one cares. It doesn't affect anything. Because essentially what we can do is we can just say, well, actually, this might look like 1 million zeros, but actually that's just the special character 0 to the power 10 to the power 6. And that's actually one character. And I'm going to create in my sigma alphabet a character that means 1 million zeros. And I'm going to write it exactly this way, but I'm going to think of it as one character. And in fact, if we look at the LaTeX for this, we'll see that it's very close to the format code for a single character, right? Because this thing, I could just say I have a new font where I press a key on my keyboard, and I get that number back. No one can stop me from doing that. So it isn't academically interesting to think of that. So we're just going to assume a tall tree, setting aside all of this notion of how big rules can be, right? And when we have a tall parse tree or derivation tree or whatever we have, every single one of the steps of that tree involves applying a rule or a variable substitution. And so we're going to have a very tall tree, which means we're going to have very many variable substitutions, okay? And when we have very many variable substitutions, and we have a very long string, we can always make our string long enough that we must repeat a variable substitution at some point. And this is the same idea as repeating a state in a finite state machine, right? We're going to do the same thing. As soon as our string is longer than can be described by using every substitution once, we have to repeat a substitution somewhere. So, how do we do that? Well, I'm going to express this using TIX. TIX is part of the LaTeX library. I had a hard time getting it to work in LaTeX inside Quarto, so I just included R, the R project for statistical computation, which I just showed you for my machine learning slides that are totally unrelated, right? I happen to have an R instance running and I happen to have a LaTeX engine in it. So I used that LaTeX engine instead of TinyTeX, which is what I used for, this is LaTeX. And then I'm going to show R. It was not super easy for me to get this to run, so I've included 2 links. This link is to Overleaf, and this is how to use TIX. This link is to Stack Overflow, and this is how to use LaTeX inside Quarto. So these were the 2 things I used to get this working. There's one thing that I don't love about this, which is that these, unlike some of the other images I've made, that is actually an image, so that means when font appears on these images, I'm not going to be able to copy-paste it. I don't like these images quite as much, but I needed to do some sort of geometric representation, so I'm using a geometric-based graphics package versus previously doing just the flowcharts. Okay, so how's this going to work? Okay, and we see our first graphic. I have drawn the very long string. So I have a very long string, and this string is named S. We could name it whatever we want. We just chose to name it s for convenience, so we can refer to it as something. And we note it is very long without quantifying how long that is. So with this very long string, we're just going to say it's long. S is long. We'll come back to it later. Because S is long, the parse tree is very high. How high? Very high. We will quantify how high later. At the very top of this parse tree, we're going to start with the starting variable of our context tree for grammar. In the examples we've been using, the starting variable has often been e, so we're going to begin with the starting variable e at the very, very top of our parse tree. There will be some large number of substitutions. How many? More than the number of states, right? More than the number of rules. And at the end of our long series of substitutions, we will end up with the string s. We have assumed s as part of the language. We have assumed the starting character is e. All of these are assumptions that are reasonable to make, and we're going to contradict them and show that they are wrong, right? Okay, so I have my very long string. I have my very high parse tree. How high? It is tall. It is tall high. It is very high. So we have a long string, which is a correspondingly tall parse tree, okay? Now, when we have that tall parse tree, that parse tree corresponds to a series of things that together constitute the derivation of s. We introduced this term derivation, that it is. The derivation is the series of rule applications and substitutions that begin with the starting variable and end with some string s. So that little squiggly line through the middle of the screen, that represents the derivation of s from e. All we're doing, it's the same context-free grammar we've used, it's the same one we used on the board. We're just going to keep applying rules until we get to s. We've also, by the way, already shown we can do this with push-down automata, right? So we have a way to actually compute this thing with our theories of computation we've introduced. Okay, so we have a long string, we have a tall parse tree, we are deriving s from e. Okay, what do we do next? Well, we're going to note that if e is tall enough, we're eventually going to run out of rules, or minimally we're going to run out of variables, the variables being the non-terminals, right? So there is not a single variable in s, but at each stage in this parse tree until the point we get to s, there's going to be different variables. And so we denote two variables r. We call them r because we have to call them something, right? There's no particular meaning to e and r other than they are distinct, but they don't even have to be distinct, right? It doesn't really matter. But anyways, there's going to be an r up here closer to the top and an r down here closer to the bottom. Could there be more r's? Yes, we don't care. Perhaps we take the first two r's, perhaps we take the first and last r. The only thing that matters is that it repeats ever. And in this sense, it is the same as the regular pumping lemma. We don't care if you go through a million states more than once. The only thing that matters is one repeated state, and we can use any one repeated state for a pumping lemma. So at some point, we will see the same variable twice. We call that variable r. Okay. So those variable r's are themselves going to have derivations, and they're not going to derive all of s. They're going to derive some subset of s, and I'm going to give that some subset of an s a name. We're going to take what I think of as here is the same sort of notion of having a derived parse tree from e. There's going to be a derived parse tree from each of these r's. I'm going to point out here what this means is necessarily we're deriving something different from r each of these two times. And that has to happen because we have something we repeat a finite number of times. So it has to behave differently in each of those two repeats. Okay? So we could have, for example, the first time we substitute r, we could substitute r for 0, r, 1. And the second time we substitute r, we could substitute r for 0. That is one way to have this. And so then our rule for r is r becomes 0, r, 1, or r becomes 0. That's all. Okay, so this is an example of one of our derivations. I'm simply going to name each of these chunks. I'm going to name the first chunk that is derived from e, and it is only derived from elements of e that do not correspond to the derivation of r. And I'm going to call that u on the left side, and I'm going to call that z on the right side. So perhaps the derivation of r is e becomes 1, r, 0. In that case, u is 1 and z is 0. That's all. Perhaps it is the case that the rule, or the sequence of rules here, causes there to be a million u's here, or a million 1's here. And perhaps over here we have a bunch of characters we've never seen before. Maybe there's a bunch of Cyrillic over there. I don't know, it doesn't affect me, right? Is Hindi written in Sanskrit script? What's the name of the script?
Sanskrit.
Yeah, so perhaps we have Sanskrit on this side and perhaps we have Cyrillic on this side, right? Who knows? Doesn't matter. The important thing is there's going to be a bunch of characters coming out of E that do not correspond to R. And so at some point we're going to have some combination of rules that results in a bunch of terminals, an R, and then a bunch of terminals, right? And those terminals are U and V. Okay, well then we've got R, and what's R going to do? Well, over time, R is going to correspond to some large number of terminals as well. But there's different combinations of terminals to which R can correspond. There's one string that can be derived directly from R, which is X. X can be derived directly from R. So perhaps that's a single substitution, right? Perhaps we say R directly becomes the full text of the Epic of Gilgamesh or something like this, right? And so this is some epic ballad, right? And then we have V and Y. And those are the prefixes and suffixes. Those are rules that we can apply to put things around R. So at some point, R is going to pass down to another R, but in the meantime, it's going to be throwing strings off to both sides of itself. And you may think, what if it only puts strings on one side of itself? No problem. That is allowed. It is completely reasonable for V or Y to contain no strings. It is only necessarily the case that one of them contains strings if not zero, and that's necessary by our assumptions. And if it were not the case that there was either a V or a Y, then it would mean that this substitution is just an R for R substitution, which means it's not actually a repeat. So we're allowed to assume this. Okay. We have a long string with a tall parse tree, and we break up the name of the string into U, V, X, Y, and Z, and we sort of break them up by their ancestor. X's ancestor is the youngest R, V and Y's ancestor is the oldest R, and U and Z's ancestor is E. Predecessor, parent, people say different things. So for my proof, what I'm going to do is I'm going to point out that I have an existing derivation of R. I've demonstrated on the previous slide that R can become V, X, Y. I know that's allowed because I have the existence proof right here. Okay? So I'm going to take this VXY, and I'm going to note I have an R right here. And so then I'm going to take this R, and I'm going to say, well, I don't actually have to have R derive X there. I can have R derive VXY again. I can use the same derivation of R that I use up here, and then I can repeat the lowest derivation of R. So I am essentially adding a generation to my ancestry here, right? Previously I had an old R and a young R, now I also have a middle R, right? And then I have my final string that results from this is U, V, a second V, an X, and then two Y's and a Z. This looks an awful lot like the pumping lemma to me, right? Because what I can do here is I can change this R again, and I can keep changing this R, which means I can add as many V's and Y's as I want. And it looks, I don't know, like a little house or something, right? So,
many, I think we can make it like U, V, X, we can add all of them, right? Or just V, X, Y?
we can definitely add Vx, or no, we can definitely add V's and Y's. This proof doesn't show that you can add U's and Z's, does it? No.
And in the first graph over there, you see
over here?
the line between the last, yes, there is two sections over. One is right X between W, V and Y.
Between V and Y?
X.
Yeah,
if
this
you
X.
see the youngest R, the triangle, yes.
Yep.
You see the line is dividing the R.
Oh, yes. This line is intended to denote a derivation. So it doesn't necessarily correspond to, it's not necessarily the case that there's two substrings of R that necessarily are derived from the same variable. And one example of that could be that the substitution rule is exactly R becomes X atomically in a single step.
So it represents just the derivation of?
Yes, it just represents the derivation. We make no claims about the derivation other than the few specific ones we have denoted, which is that we say, on the way to S, E passes through R twice. And we've proven there is at least some R. Now, I think you've mentioned repeating U and Z. That is certainly the case if E is what is repeated, but we have no guarantee that E is the thing that is repeated. We don't know that the starting variable repeats. We just know that some variable repeats. If it is the case the starting variable repeats, no problem. Then you can have as many U's and Z's as you want, right? And in fact, there's probably forms of grammar for which that is true, simply not this form of grammar, right? Okay, so we have them side by side here, and I note that I could keep stacking these up as many times as I want. It got quite tedious. All of these lines are hand-drawn on a coordinate grid by finding their coordinates, so I was getting very tired of doing mathematics. And so what we point out is on the left we have U, V, X, Y, Z. We do not know E repeats, so we don't know that we can repeat E, U, and Z, but we know something repeats. And since something repeats, we simply call that thing V, and then we can have two V's. There should be two Y's there. That's interesting. Oh, I don't even have Discord open. Okay. I need some good way to take notes about the errors. Like, what I want, I don't know if you, like, what your experience with web dev is, but I want to, like, report bug button right here that just opens an issue on GitHub to this page. And I'll come back and I'll figure out what the error is, right? But yeah, there should just be two Y's there. And there's no reason to forget that Y. I don't think in this case it looks confusing because I specify what I mean immediately in the next line. It's just, that's just wrong, and I don't like that it's wrong. Okay, so we have two V's and we have two Y's. Okay, no trouble at all. And I know what you're thinking. I don't. I'm going to pretend that I know what you're thinking. You're thinking, wait a minute. You said we could also have 0 V's and 0 Y's. Is that what you were thinking? Oh, you could have said yes, right?
Yeah, I was thinking like...
Oh, that is what you were thinking. I knew what you were thinking. Okay, all right, well, because that's what I was thinking too. So we're going to have to deal with that problem. Before we deal with that problem, I'm changing the geometric classification of this, so I'm converting all of these to exactly 45-degree angles and so on. This just makes things a little bit easier to look at. I also want to show you what this code looks like, and what you'll see are these are simply lines where I have a starting point, and then I have a distance in the x and y coordinate plane. So these are relatively easy to draw if you ever need to draw one of these for some reason. I have specified my fill color is dark gray, and then I draw a series of white lines on top of it, and this is just LaTeX. So you can adapt both of these to your uses, and you'll note that I put some text in cyan. What's that text in cyan? Ah, the letters are in cyan, right? And then I was also using orange when I said long and tall. So this is fairly simple to compose graphically if you're interested in that. Okay, this is the question you asked about so astutely. You noticed, hey, you said I can take out all of the V's and Y's, and in fact I can. I simply say that the first R is the youngest R. There are no other R's. We do not repeat R at all. And when we don't repeat R at all, the thing that R becomes is X. X is one of the things that can be derived from R. So simply, I take whatever the derivation was to get to the first R, and I replace V, X, Y, which R can derive, with X, which R also can derive. See, even just over here, it's simple to see that R can either become VXY or just X. So I put just X there. We don't worry too much about any of these things, and this is U, X, Z, and it perfectly becomes the derivation of UXZ, which is the one other thing I needed for my proof. And so I say that this proof by picture constitutes a proof of the context-free pumping lemma. We could exhaustively go through here and do everything with actual grammar theory, but I don't even know how it would be different. We would essentially just be writing down what these pictures show, right? You could, of course, write a program that when given some sort of computational specification of a context-free grammar determines what U, V, and X are, right? And one way to do that is it could simply start deriving strings until it finds a satisfying string and then pumps that string. And in fact, that would perhaps be an interesting programming assignment to do, and perhaps I will assign it, right? But that should not necessarily feel more or less convincing to us than these pictures. I think one of the advantages of actually doing this with a computer program is if we can convince ourselves that the program we've written is equivalent to a context-free grammar, then it provides an existence proof. But it only provides the existence proof in the context of one language. And it is difficult to prove the correctness of a program, in fact impossible, and that is the subject of this class. So we have a recursive problem if we start trying to prove this by writing programs, right? But it's nevertheless academically interesting to write such programs, right? So let's look at some details real quick. we're going to need to figure out what P actually is, and the way we do that is we find the maximum branch size. What's the maximum branch size? Well, every substitution is going to add at most some number of terminals, right? So I gave the example of the substitution that adds 1,000,000 terminals, right? I don't care how big that number is because it's finite, and I just say that number is B. And I'm going to do everything related to B. So whatever my pumping value is, it's going to be some multiple of B, right? Then I'm going to say H is the height of my parse tree. Do I care how big H is? No, but I know it's more than the number of my rules, right? So I'm just going to take number of rules plus 1 times maximum amount of terminals I add per rule plus 1. Multiply those two things together. And that's all. That's enough. Oh, right. It has to be to the power. And why does it have to be to the power? Because then I have two substitutions at the same height. I can do two substitutions at the same time. And so if I say I substitute E for E plus T, or what is it? If I take E and I substitute that for E plus E, then at the next height, each of those E's can then branch as well. So that means at every height I have exponential growth in how much my branch can grow, which means that if I also have a rule that says I substitute E for 1,000,000 zeros, I can substitute a lot of E's at a very low point in the tree. So we'll do the exponentiation here. But you don't even have to do this. You just throw a factorial in here and it's still a finite number. It doesn't matter how big this number is, right? So there we go. We're going to let P equals the branch size to, and we're not going to use the rules here. We don't care about the rules. We only care about the number of variables, the non-terminals, the things that could be on the left-hand side. Because we don't have to repeat every rule. We only have to repeat a variable in order to make this happen, right? When we look at this proof by picture, right, we are not talking about which rule is used here at any point. We are only saying we have the presence of the same terminal. That's all we need. So we're going to take the maximum branch size to the power of the number of variables. Easy. Okay, all conditions. We always have to be able to pump any amount of numerical times, so we can't pump a negative number of times. That doesn't make sense. What is a string of negative length, right? Perhaps we could define strings of negative length, but is that even interesting to do? We're essentially going to say that this is by cut and paste argument. We're going to denote that V concatenated to Y, the two things we're pumping, they cannot together be the empty string. Either one of them may be the empty string, because perhaps all of our substitution rules only prepend to terminals. That's fine. That's still a context-free grammar. And in that case, we only use V or Y. And in fact, it would be simple enough to say, we have two pumping lemmas, one for when you prepend and one for when you postpend. No one cares. Okay, we're going to take the smallest possible tree. And the way we're going to do this is there could be some rule that substitutes R for S, then substitutes S for R, then substitutes R for S, then substitutes little sigma for R or S, whichever one we have, right? So we say, fine. If such substitution exists in your derivation, we're going to simply assume that there is some other equivalent derivation that doesn't contain such a loop, and we're going to use that derivation. No problem. So the way we solve this problem is we simply say, we will always take the smallest possible derivation of any string. Now remember, in our proof statement, we only talked about the string. That some grammar existed. We didn't say which grammar. So this is only a proof about languages. Languages can correspond to more than one context-free grammar, as we showed with A plus A times A. We showed two different grammars for that. And so since we only care about languages, we just say, we're going to take the well-behaved grammar for our language. And then it must be the case that VXY, the middle, the lettuce, lurker, patty, and cheese. I should pick an example for us because we're vegetarian, but it's the only sandwich I can think of, and I did just have a vegetarian burger. It was vegan too. Had jalapenos on it, and I think they made my stomach sick because I'm a lightweight. So, yeah. Do you like jalapenos?
Yes.
Yeah. I thought I did too, and then I ate a bunch of them. I was like, ugh, I'm weak. Okay. So we're going.
It's lots spices, like all.
Yeah.
Anything related to spicy, jalapeno, if you can, masalas, and everything.
Yeah.
I'm purely vegetarian.
Sorry?
I'm not.
Yeah.
I'm not purely vegetarian.
Oh, okay. You just maybe prefer it most of the time.
Prefer most of the time vegetarian. It's when I was a kid.
Yeah.
My grandfather didn't like me to eat vegetables because in India it is saying that if you eat non-veg, that means it comes from I don't know whether it's true or not, because at the time only kings or like royal people can afford meat at the time. So my grandfather always have meat.
It's like I'm one of the royal people.
From the royal. So whenever I go to visit his house, I always eat meat. So I'm getting like bored of my childhood. I have eat non-veg every day. So he has a thinking like that. I don't know. I still have it.
Yeah. You know, so like one of the reasons I don't eat meat is my grandfather. He had a job slaughtering chickens during the Great Depression, and I guess it was absolutely miserable, and he just stopped eating chicken as soon as he had enough money to stop eating it, which means that my family grew up not eating chicken, and so none of us have the taste for it, so it doesn't taste like food to us, and that's how we all ended up. Like, it's funny how these just like, you know, I don't think our like grandparents think like, oh, I'm going to give this person a strange diet for the rest of their life, but they do it one way or another, right? Like, and there's nothing wrong with that. It's just, it's funny how it happens. It's funny that for both of us,
We're different.
yeah. But like not even that different, right? Like in both cases, it was like, oh, we don't want to seem like we're poor, right? And so perhaps when my grandfather was growing up, he perceived chicken as for poor people, and your grandfather is.
In India, back in the time, you know, the meat, chicken or beef, anything, it was expensive at that time because most of the Indians are vegetarian. So it's a privilege to have meat in your house. Maybe that's why.
Yeah.
You eat vegetables only when you are sick.
You eat vegetables when we're disappointed with you.
Disappointed me. He doesn't know about that.
Yeah.
I don't eat.
Well, your secret's safe with me.
Yeah,
I won't tell anybody. Yeah. And also good for you just choosing to eat what you want, right? It's good to make our own decisions. Okay. All right, sorry, back to work. It was fun talking about vegetarian food. But we've got a pumping lemma to pump.
Yeah.
And this pumping lemma is over 0, 1, and 2. And we have k such values of each. And we said we long suspected that this was not a context-free language, but we didn't have a way to prove it until we did the pumping lemma. So, no problem. Let's do the pumping lemma real quick, right? How hard can it be? So, what are we going to do? We're going to notice, first of all, and this is the first thing I notice when I look at 0, 1, 2. That doesn't break up into 5 parts very easily at all, right? And I'm going to have a u, a v, an x, a y, and a z. And I don't know exactly where they're going to correspond to in there, but it's already looking to me like there's not very many places I can pump this, right? So one of the natural things I would do is I say, perhaps I take k over 2 zeros and ones on one side, and perhaps I take k over 2 ones and twos on the other side. Well, then there's no x, because I took all of the ones. And then you say, oh, okay, perhaps I take k over 2 zeros on one side, and k over 4 ones on that same side. And then perhaps I take k over 4 ones and k over 2 twos on the other side. And maybe I can pump that right. But then that doesn't satisfy something else, which is that vxy, the middle, has to be less than p. And I can always pick one that's less than p by just picking the lowest substitution, right? So somehow I have to get 0, 1, and 2 in vxy. And that's because if I repeat any ones at all, I have to also repeat ones and twos. vxy has to be less than or equal to p. So that's one of my assumptions, right? And so, well, there's nothing I can pump then, right? Because I just set k equal to p, and this is unpumpable, because then I only have ones in the middle p characters. So, no matter what, if I set k equal to p, this doesn't work. It's not in CFL by this condition, condition 3. And we assumed this condition, we demonstrated this condition convincingly by saying, you just take the lowest substitution. So this is an example of something we can quite easily prove is not expressible with a context-free grammar. And so that's just the application of the context-free pumping lemma. You can do all of the fun, exciting things with the context-free pumping lemma you did with the regular pumping lemma, where you can combine it with closures and stuff. But I will note we do not have very many closure properties here, right? Mostly the use of the context-free pumping lemma is to show that things cannot be expressed with context-free languages when we're talking about acceptance and emptiness. Okay, I have to see what time it is because I can't tell time. It is 1:33. Oh, someone's texting me. Is it important? Okay, no. Ugh. Did you have a cell phone growing up?
No.
Yeah, I miss that. Now people can find me at all times.
I had a phone call, cell phone, when I was in final year of my high school.
Yeah. I won't say they're not useful, but I don't know that I love them. Okay, it's 2:30. This was supposed to start at 1:30. Probably the way to sell this is we cut the review tomorrow or something, or we just go faster. I want to grab some more coffee because my throat's getting sore.
Yes.
So let's take 5 minutes.
I'll use the restroom in my
Cool. Oh, my leg's falling asleep. Oh, rookie mistake. Oh.
You sit too long like that?
Yeah. Well, you get really excited about the context-free pumping language and you forget how uncomfortable you are, We were, we were working really hard on this all day. Okay, so we'll start with Turing machines, and yeah, I don't know. We'll see. I'll just pull the pumping slides back up again if we need them as well. But I was thinking about it while I was making this. I was like, oh, in a way, this is a context-free pumping lemma. And I was like, no, it's not. There just happens to be a pump in there. Like, there's no actual similarities, but you know the similarities in the words. Okay, so let's do some Turing machines. I've introduced 2 grammars and 2 automata so far, and each time I've given a few different ways to view them. In the case of the Turing machine, we're going to give a schematic and we're going to give a formal definition. And it may shock you to learn that the formal definition is going to be a tuple of about size 7. I don't remember if it's exactly 7, but I think it's 7, and I think I know what the parts are, right? And it probably is going to come as no surprise to you at all that the delta function is going to be considerably more complicated once again, right? Okay. So, Turing machines, what are they? Well, right around essentially the 30s, I think, basically what happened is mathematics in Western Europe and the United States. Turing was British, and he studied in, I think, New York. I think he only finished his undergrad or something, and it was the 1930s, so that wasn't even different than a PhD or something. What's going on here is right around this time, automata and language theory is basically narrowing in on being a closed research area. There's not that much of interest left going on with finite state machines. And of course, there's these open problems like, hey, can they factor numbers? No one knows. We still don't know. We don't even know how hard that is. Perhaps someday someone will prove it's impossible to even prove that you can factor numbers, right? But we've completed 12.5 hours of automata and language theory that essentially correspond to getting us up to 1936. In 1936, the world changes because the Turing machine comes out and people understand it. It's not new, but they understand it, right? And so what this corresponds is to our understanding of these 3 things. We're able to differentiate and define the finite automata and regular expressions, which are equivalent. And we're able to demonstrate correspondences between them. And we should also be able to describe the same features of the push-down automata and the context-free grammars. We should also be able to use the pumping lemma for both of these, right? So on the syllabus, I promised you I would teach you these 2 things, and I'm claiming I have taught them now, right? So now what are we going to do? We're going to go on, and the Turing machine is still an automata, but it's also something else, which is a computer. It's the overlap. It is both an automata and a computer, right? And so now we're not thinking about, we are still thinking about automata theory, but not really. We're thinking about computability, because anything a Turing machine can do, a computer can do. So it's the same thing. We just use a Turing machine as a way to describe it. And in that sense, the Turing machine is actually very similar to the push-down automata, which is everyone actually uses context-free grammars, but they do proofs with push-down automatas. Everyone actually uses an Intel x86 64 assembly, or many of my students have Mac M1s, but it's not as if Intel and Apple are making Turing machines, right? But if we want to prove something about a computer, we're not going to prove it about the x86 64 instruction set architecture, because no one can do that, right? But Turing machines we can think about, right? So we have finished laying the groundwork to understand the Turing machine, so now we're going to understand it. Okay. Turing machines, almost always called TMs. Nobody has time to write Turing machine. Remarkable shift to me in the sense that this one is named after a person. And this is one of the times I think it's actually maybe kind of reasonable to name it after a person. The Turing machine is considerably easier to understand than the Post machine, which was almost example. So it seems like really only Turing figured this out. And it doesn't seem like in the 90 or 89 years since then someone has come up with a better model than the Turing machine. So I think this was maybe more of a core insight. And we can contrast this with the context-free grammar that someone in India came up with 2,500 years ago and has basically been the same since then, and wasn't formalized until Chomsky came around and bothered to formalize it, and still no one uses it, right? So we're not going to name context-free grammars after Chomsky or Panini, but Turing's the only one that got this. And I still have a preference to not name things after people, right? And that's why I have a tendency to among other things, the lambda calculus, because it doesn't have this problem. But if you just say the lambda calculus and you don't say Church's lambda calculus, no one even knows what you're talking about anyways, right? So these are Turing machines. One of the other equivalent formulations is the recursively enumerable languages. That's another one that doesn't have someone's name in it, right? So these things are equivalent to Alonzo Church's lambda calculus. Alonzo Church put together the lambda calculus in 1930, and I believe it took until either 1933 or 1935 to make it consistent. So he had an idea, and he wasn't actually able to write proofs about it because the idea took so long to make sense. And then when you think about, like, well, why do we use Turing machines? It's like, well, the person that came up with the next best formulation, which is usually considered the lambda calculus, while he was inventing it, while he was teaching Turing, who came up with the Turing machine on his own, right? Alonzo Church couldn't even understand what he was doing, right? So, like, maybe we shouldn't assume we can understand the lambda calculus. Now, it so happens I looked at the lambda calculus and it made perfect sense to me, but I'm not going to assume that happens to anyone else, right? Because I remember my complexity instructor speaking to me that said, you'll never understand the lambda calculus. And I was like, I don't know, I think I do. So maybe I'm wrong. I really like the lambda calculus. You will never meet anyone else who likes the lambda calculus. Everyone hates it except me, including Alonzo Church. Okay. Kurt Gödel's general recursion has the exact same problem. Absolutely no one likes this. I don't even like it. I do still like it better than the Turing machine. I have a really strong bias against the automata. To me, they don't make sense. But I was shocked when because I remember learning the first times about the Gödel's general recursive functions. I was like, oh, these make so much more sense. And then, like, the next paragraph in the book was, and Kurt Gödel stopped using them as soon as he heard about the Turing machine. I was like, gosh, dang it! Like, has anyone ever written proofs in this? And then I think also one of the reasons I have these biases is I don't think I try to write particularly challenging proofs about them, right? I just use them to express sort of abstract concepts in a way that's clear. And I think actually probably the lambda calculus is an okay way to express a program, but you would never want to prove anything about the lambda calculus. And I think that's where Turing really comes in. Emil Post's model is identical to the Turing machine. The only difference is Emil Post was much more rigorous about requiring things like the letters be expressible in binary and stuff. It turns out every single one of Post's differences was later proven to not matter. So all of the assumptions Turing made have now been proved reasonable. But I think in 1936 this was probably not immediately obvious, and it was probably of great benefit to everyone involved that Post came up with this same model at the same time, and Post's model was much, much more defensible if it was harder to work with, and they looked quite similar. So I think Post is probably underappreciated for that reason. We should probably be considering calling them the post-Turing machines or something like that. And I have seen them called post-Turing machines. One of the other problems with that is post is a prefix in English, so people think that means the machine that comes after the Turing machines. And so I think that's the real reason they're not called post-Turing machines, is because it's confusing. And you can't call them a Turing post machine because post is also a noun, and it sounds like a machine that does posts, right? So poor Post. With the first time I saw Turing machine, I thought it was a typo for Turing machine.
Turing machine.
Yeah, I was like, that's weird they left the N out. Okay, there are more than one ways to visualize a Turing machine. I'm going to go as far as to say this is the way you should do it, which is an unusually strong claim. And why is that? These are matters of extraordinarily high complication. I'm not going to say complexity because that's a word we use for something else. And just getting everyone on the same page about understanding them was done for a reason. I've sort of motivated the other people that were smart enough to generate equivalent formulations, all deciding to use the Turing machine because they could think about it. So, as with the push-down automata, the Turing machine has a head. I think of the head the same way I think of a vinyl player head, or the head of a hard disk drive, or the head of a cassette player. This head we are going to denote as, perhaps being an arrow, and it is going to be an arrow that is going to point at a specific location on a tape. It is going to be reading a specific letter, the same as the push-down automata. Okay, so similar to the push-down automata so far. In this case, I have stylized the Q1 here to denote that the finite control of the Turing machine is currently being represented as a state denoted Q sub 1. That is the same as a finite automata state, or that is the same as a push-down automata state, right? But in some sense, there's some finite control in here. That's all that's going on. Okay. Now, this tape is infinite. My understanding is that the first models of the Turing machines assumed that it started at a point and then continued to infinity, so it was a bijection to the natural numbers. It was very, very simple to prove very quickly that you can assume the tape goes infinitely in both directions. And in brief, I'll say, well, you have an alphabet with, for example, 2 letters, 0 and 1. You simply create a letter for all combinations of the alphabet, and one of them is for the letters going in the other direction. So you imagine the starting point is then 0, and if you have in position 1 a 0 and in position -1 a 1, you simply write 1 0 in the first box. And that only expands your alphabet size to the squared power, which of course is within reasonable amounts to expand your size of the alphabet. We've already expanded alphabets by exponential factors in other automata. Okay, so one of the other special things that's going on here, there's a special blank symbol. And so we are going to have boundary conditions. The tape is potentially infinite, but we can tell when we go off the ends of the parts that have been written to. There are now 2 different things that can write to a Turing machine. With automata, we have always assumed that someone gives us a tape with some letters on it. And that is a reasonable assumption for a Turing machine as well. But a Turing machine can do one other thing, which is it can start with a blank tape and start writing to it. So the Turing machine can read and write, and it is the first such machine that can do so. The push-down automata can write to the stack, but not to the tape. The Turing machine can write to the tape, which means you can give it a blank tape and it can start generating something. This is one of the reasons that at the Turing machine level, we're not going to talk too much about languages. We're only going to talk about Turing machines. A Turing machine is both a recognizer and a generator. And it is the first automata with the power to do that. And that's one of the reasons we don't call it an automata anymore, even though it's based on it. Okay. Q1 in the head denotes the internal finite state. The array, and I always express them as arrays because it's important there's fixed locations on the tape. The tape is discrete. It is not continuous, even though it is infinite. So we're going to take the tape to be denoted the exact same way as the schematic model. And I have the zeros here, and specifically all of these zeros to denote the special blank symbol, right? So most of the tape is blank, which just means there's nothing written to it. Sometimes we need to use a symbol to denote that. You can use the null set, you can use 0, you can use B here for blank. You can specify that however you want. The only important thing is that you know what it means. I think we can look at this, and we can say, oh, hey, you know, this person that made this for Wikipedia, like, had some internal notion of what this means. And we can even just probably see where it's used on Wikipedia, and there's probably a description of it. Can I even find it? Not really. Oh, wait. Did one of these say? Where's English Wikipedia? There you go. Turing machine. Someone actually made a physical one, which is kind of goofy. And here we have it. The blank in pre-field was 0, and then we write non-blank symbols including 1 and B. Okay. One of the things, and the way I visualize this and didn't, oh, I have to go back many times. I didn't realize I didn't open that. I have this coloration here, and that denotes that the head of the Turing machine can currently be reading a blank symbol. So it is possible for the Turing machine to go an arbitrary distance into the blanks without reading or writing, and then come back. And that's perfectly legal for it to do that. There's not a lot of times you want to do that, but very frequently you want to go a little bit off. My impression is that this was widely regarded as not a reasonable thing to do. And then what happened is the 64-bit AMD architecture came out, like 2008 or something, a few years after Pentium. And its internal model for the stack data frame that it was using in its cache architecture and its program memory, they allowed you to use negative addresses with respect to the cache, and you just write off the end of the cache. And it's all just maintained internally. So they were writing to what is essentially blank symbols on the closest thing they had to a tape, which was computer memory cache, right? So I think, like, my impression was for like 80 years, people were like, oh, that's so weird, you can read off the end of a Turing machine. And then in 2008, AMD 64 just implemented reading off the end of the Turing machine, and it led to dramatic increases in performance for the 64-bit architecture. So there's a lot of these things where it's like, yeah, you can do that, but we don't know why. And then, like, 80 years later, you find out, oh, that's a massive performance increase if we do that under this one specific circumstance that didn't exist 80 years ago, right? So I am going to point out for that reason that you can do this. And I think, like when Professor Sipser teaches this class in my class in undergrad, most of the people that teach this class are formal mathematicians, like we were talking to Professor William Yen, right, who's a formal mathematician, right? I studied hardware architecture for years, and it's stunning how many of these little things where they're like, oh, you can just assume you can do that. So I was like, no, we don't assume that, we do that. Like someone went in and implemented that in electrical engineering. And I don't know if they knew about Turing machines or not, but like that exact model you can do. And non-determinism is the first example of this, but running off the end of the tape is the other example of this. We can just write to memory spaces that don't exist and hope it cancels out, and frequently that works, right? So we have some internal state. We have the non-blank tape symbols, 1, 1, and B. And then we have the head position. I haven't seen a lot of people do this. I frequently see like English language proofs that say, we begin before the first symbol. I don't do that. I use Python array indices. This is the -1th position, right? Because that is the 0th index of the array, that is the -1th index of the array. And actually, I guess I just should say that's not Python, because the -1th index of the Python array would be right here. But this is the -1th position of the C language array, right? And in fact, in the C programming language, I can put -1 inside one of these, and it causes the program to explode, but it is in fact possible. I'm allowed to write that there, right? So let's continue to think about this. The head can read and write. It can do something that the push-down automata cannot do. But it can do something that the actual existing physical heads and hard drives can do. This was a completely reasonable thing for Turing to assume that heads could do, and in fact they could by this time. Your gramophone that you saw growing up, that could not read and write. Turing knew someday they could somehow. Good for Turing and good for Post. They both realized this, right? I imagine they were probably thinking of like a human librarian manipulating something and then moving on to the next thing or something like that. But it doesn't really matter if a person does this or a piece of electronics. Right? Okay, the head can read and write. The head is two-way. This head can move to the left, and it can move to the right on the tape, and it can move infinitely in either direction. Completely different. The push-down automata can only go forward. The finite automata can only go forward. The Turing machine can go back and forth, which means it can write itself a note, go do something, come back and read the note. And that's what causes it to be Turing complete. And that is the same thing my physical computing device can do, where it can write something down in instruction cache or memory cache. It can write something to a hard disk drive or a solid state drive. It can push something out onto the cloud and read it later. So it can leave itself notes everywhere and then execute conditionally upon the values in other places around. And it can access all these places at the same time, and it can read from the cloud and the hard drive and the solid state drive and the cache and the RAM all at the same time, right? That's what a Turing machine can do. Completely different level of power than a push-down automata that can read one symbol from memory. The tape is infinite. We are now able to accept infinite languages, good for us. And there are always infinitely many blanks after any input we provide to the Turing machine and after any output we provide to the Turing machine. This felt impractical to me when I first learned it as well. I have since learned that in Python 3, the integer data type is infinite precision, which means those numbers take potentially infinite amount of memory, and you just happen to only use the low-order bits, and then Python tells you when you can stop reading. Well, that's the same thing as a function returning something of infinite size and just saying stop reading after you get this far, right? And this is actually the same as the C language null terminated strings type. So this felt very strange to me when I first learned it. It's like, oh, all of the outputs are of infinite size, they're just followed by infinite many blanks. But actually that's a completely reasonable way to express things. We haven't covered it in this course, but the infinite version of the finite automata, the Bushi automata that accepts the infinite strings, they use this same notion where they say the end of a string is when you start infinitely repeating a symbol infinitely many times. This just always repeats the blank symbol specifically. But with 0, 1, 1, 0, 1, 1, we can just say, there's an infinite number of ones at the end of that. It won't affect anything. All we do, and we already have it here, we already have a self loop on our accepting state that accepts ones, right? Yeah. Okay. What that means is it becomes very hard to accept strings that terminate with something because all of your strings are infinite. But that's okay. The push-down automata and the finite automata, their acceptance or rejection criteria is based on what the state in their finite control is when they reach the end of the string. The Turing machine has no equivalence to that. It can accept or reject at any position. It can turn on, read 0 symbols, and instantly accept or reject. What this means, it is now dramatically easier for the Turing machine to accept the universal string, or the universal language that contains all strings. It says, I turn on and I accept without reading anything. It is also much easier for it to reject anything. So we had the reject all string that accepted only the empty language, right? We had to say, okay, so you don't read anything, you go to the accepting state, all of this, blah, blah, blah. Turing Machine doesn't do that. It says, my return value is yes. My return value is no. It doesn't have to do any internal computation. It doesn't have to read to the end of the string. It doesn't have to do any of those things, right? So that is much easier for us. Okay, here's an example. We have a to the k, b to the k, c to the k. We've seen this previously with 0, 1, 2. Let's see it with a Turing machine. I'm going to specify as the 0 step begin at the leftmost location. That leftmost location, remember, we go infinitely in every direction. So I'm beginning at the leftmost sort of printing character, or the initial character of input, right? And it is easy enough for me to find that, right? Because the Turing machine can simply start at a fixed place and then go progressively far to the left and right until it reads input and then read to the leftmost position of the input. So it doesn't matter where my head starts, I can always find the leftmost position of the input. When I begin at the leftmost position of input, I'm going to scan right until I see a 0. And the 0 is the blank symbol. So what this means is I'm going to read all the way across the string. But I'm going to do one thing while I'm doing that reading, which is I'm actually going to perform something known as type checking. I'm going to make sure that I only read A's until I see a B, and then I'm going to only read B's until I see a C, and then I'm going to only read C's until I see a blank. And if I see an A after a B, I'm going to reject immediately. And if I see a B after a C, I'm going to reject immediately. And if I see a 7, I'm also going to reject, because that's not part of my language. This is very useful to us because it's easier to think about. Because now we don't have to think, ooh, what if there's a B in the middle of the A's? No, I already checked, so now I'm going to write a very simple loop, and all I'm going to do is going to count A's, B's, and C's. Okay. I'm going to return the head to the leftmost position. And I'm going to run along the length of my string, and I'm going to overwrite one each of the A's, the B's, and the C's. I'm going to delete one of them, because I can write now. So I can either put the blank character there, I can put an octothorpe there, I can invent a new character, I can put a 7 there. I'm allowed to use 7s. I can use whatever finite alphabet I want. And so I read over the list, and I erase one at a time. I erase an A, a B, and a C. And I don't erase 2 C's. I erase exactly one of each of them. Okay? And I keep doing this. I go all the way to the left, and then I run to the right, and erase exactly 3 characters. And I do that until everything is blank. And if at the end of this my tape is blank, I accept. And if there's 1 character of any of them left, I reject. Easy. Understanding check. What does cross off mean? I said I can cross these things off. How do I cross them off?
You can go by the cross off. What do you mean by the cross off?
That's what I'm asking you. How would you do this? Have Python open? I'm trying to learn to use terminal instead of command. Here's my tape. I'm going to use 0s, 1s, and 2s because they're easier to type. Okay. So the scroll to the end is not too hard. I just say not 3 in tape. Okay. So I know there's no 3s in there, right? And perhaps you do that for every other language, right? So if I want to see that there's exactly the same number of 0, 1s, and 2s in here, one of the ways to do that is to cross them all off, right? And because the Turing machine can read to any position in this array, and it can write any value to any position in this array, how can it do that? How can it change them to be considered crossed off? Let me try phrasing it this way. So I've given you this Python data structure I'll show you. Imagine this is like an interview question or something, so they give you some restrictions. And they say, you can read this list as many times as you want, but you can only read it start to finish. And you can't use any local variables. How do you tell if there's the same number of zeros, ones, and twos? And so one way to do that is to say, well, I'm going to read it from start to finish, and I'm going to erase 1, 0, 1, 1, and 1, 2 each time. And we can do that, and it's not too painful in Python. I'm going to write a lambda expression, and I'm going to show you what I'm thinking of. So I'm going to say, we're going to call this one pass. We're going to do it one time. It's going to be a lambda of the tape. And we're going to take the tape, and we're going to say tape.index of 0. That's going to return some numerical value, right? It's going to return the position of 0 in the tape. And specifically, it returns the first position of 0 in the tape. Does that make sense?
Yeah.
Okay. So that is, and then I'm going to say, well, I'm going to take that location of the tape. And I'm going to say that's equal to a special value. I'm going to say it's equal to none. Okay?
Okay.
And then actually, you know what I'm going to do? I'm actually going to do this for I in range 3, which I think is 0, 1, and 2. I can't not use a sign of expressions with a subscript. That's sad. Ooh, can I do just this? Do you know of a way to set the value of an array? Can I do like...
I think it double equal to, try double.
Well, double equal is equality, not assignment.
Or
Tape dot set 1. Oh well. I'm just going to copy paste, which is, I hate to do it, but otherwise I have to look something up. Okay, so we have one pass. One pass is a lambda operation. Ooh, no, it's not. Look at that. This is returning things it should not return. That updated tape, didn't it? Yeah, okay. So what we're going to do is we're going to put these inside friends. We're going to say that equals null or none. We're going to set all of these to be equal to none. Is that allowed? That's invalid syntax. We're going to try walrus operator. It's possible you just have to do this inside a function. I just don't know how to do that. Yeah, okay. Sad. Okay, def one pass of tape for I in range 3. Tape dot index of I equals none. Okay, one pass is a function. Okay, and we have our tape. I'm going to make a copy of the tape and work on that. Is that okay? Okay, so I'm going to apply one pass to the copy. And what's this going to look like? Well, now if I look at the copy, I have blanked out 3 values. Do you see that? Does that make sense to you?
yes.
Okay. I'm going to do it again. I'm going to blank out some copies. I can do it again. I can do it. Oh, I can't do it again. This is a Turing machine reject, right? That's a value error.
One is not a list.
It's not on the list, look.
Because we only have
There's only twos.
twos.
Everything else is gone, right? So this value error, right, this looks like an error to us in a modern programming language, right? What that actually is that's an undefined transition in a Turing machine's finite control, which exactly corresponds to returning false. I could just as easily have come back up here, wherever I define this thing, and written try, except, return false, blah, blah, blah. I don't believe in handling errors. I just write code with bugs in it. So here you go. There's my value error, and that constitutes a none. And then, we can do, I think this can actually never return true, because, let's see, we're going to make small, which is going to equal 0, 1, 2. 1 pass small. And so this is going to give a value error no matter what, so I do need to do a try except for that. That said, if 0 is the thing that's not on the list, then all I have to do is say, let's see, you just look at small, and you can say, and make sure everything in there is none, and that will return the same thing. So if you get a value error, you can say, try except not any small. And that'll work as well. So this is one way to think of Turing machines. They're running over an array. Usually it's easiest when we're describing them in English instead of Python to say you do one thing each time, because one thing I do want to impress upon you is you can probably think there might be a way to write some variables down, but remember, if you write down, for example, how many zeros you've seen, you have to write that down somewhere on your Turing machine, on your tape. And you can write to the tape, so you're allowed to write somewhere. And you have to figure out a way to express potentially numbers of any finite size with a finite letter alphabet, which means you're probably writing in binary, which means you're telling this Turing machine how to read an A and then go increment a binary number somewhere else. And you're telling it how to make sure it finds the binary number that corresponds to A's, B's, and C's, right? So you can use variables in a Turing machine. They're powerful enough to do that, right? And never in a million years would you do that voluntarily. To me, one of the benefits of teaching this type of programming is I see students use variables all the time to write worse code, and it is fine to use variables to write better code. I think one of the things that's difficult to do is to find balance in when should I use a variable versus when should I write good code, right? I never want you to be computing something more than once. I never want you to be traversing an array more than once. But I also don't want you to be using variables to just store values that aren't meaningful or don't mean anything. Attaching some notion of thinking about how much intellectual cost or computational cost it would be to using an additional variable is something that makes sense. And it really makes sense in embedded systems programming where you might have exactly 16 registers. And if you store the 17th variable, your code performance slows down by a factor of 10. And this is a real thing that happens, and it probably happens in automotive. And Kia over there makes 40% of the automobiles in the United States, so it matters probably a lot to them. I'm guessing they solve their problems by buying faster processors, but they could solve it by hiring better computer scientists, right? So that's our plan. So that's how we cross things off. Let's do the formal definition real quick. Okay. Let's make things easier on ourselves. You've seen all of these before. Finite states, input letter alphabet. What's gamma?
Gamma is the...
It's for the stack, right?
Stack,
It's the stack
yes.
alphabet. These things don't have a stack, but they do have an internal alphabet, right? Delta, it's going to be some transition function, right? It's going to read some combination of things and produce some new thing, right? The thing that's going to come up with delta that's going to be interesting is now delta is also going to tell us which direction we go on the tape. That's going to be the only difference.
So in delta, going backwards or...
And we usually say left or right now.
Left or right,
Yeah. And there's compelling reasons to say left or right in the sense that it's like not always clear what forward would mean.
Oh.
Right?
Yeah.
That's why we say left or right. But like if you personally in all of your proofs you want to say backwards and forwards, that's no trouble for me, right? I can read that proof, no problem. We have one starting state. That's just the state it's in when it turns on. We have the accept state, and we have the reject state. We compel them to have one of each. Right. So input alphabet, the tape alphabet. So what is the difference here, right? I can give a Turing machine a tape that has characters on it that it's not allowed to have when it's done thinking. So this is the same notion as the context-free grammar, where internally the context-free grammar can have all of the variables. So can a Turing machine. It just has to promise that before it returns, it replaces all of those variables. And so that's the difference between the input alphabet and the tape alphabet. The input alphabet is a strict, well, I think it's a non-strict subset of gamma, actually. I bet that should be non-strict. Simply put, you're allowed to put things on a tape for a Turing machine that it can't write. This is very simple technologically, which is this is read-only memory. Perhaps not as bad as it looks, right? Any letter on the tape to any letter on the tape, and the internal state. Yeah, so internal state and any letter on the tape, internal state and any letter on the tape, and then it goes left or right.
Left or right.
And I think there's been notions of Turing machines where they can also decide to stay in one place, and I think that's like logically equivalent. Like no one cares. Like you can stay in one place, you can move. Usually we say you're not allowed to move by a fixed number of spaces, right? So you can't say, oh, I'm going to move 10 spaces to the left. That's a little bit cheating, right? That sounds like you're not really thinking through what your code does, right? But in fact, right, in modern code, we do have jumps where you jump to a specific address where you say, hey, if this, go here. And we have go-to statements. We can debate the merits of that. Essentially, we read a state and a letter. We return a state, we return a letter, and we return a direction. Not bad at all. We're going to introduce a term, and this term matters a lot. One of the most important things in the universe is something called the halting problem. Have you heard of the halting problem? No. So the halting problem is the notion that there is no way to tell if, given some program, a computer will ever finish running that program. Here's a good example. Will this ever return? We don't know, right? Because at any time I could do that and then it does return, right? Oh. But maybe it doesn't. There's no way to tell without knowing what the input is, without simulating the entire machine.
Okay, yes. Now I get it.
Yeah. Here's an even worse one. Okay, this one seems to go forever. But in fact, there are a series of input characters I can put in here that can stop this, right? So it's ambiguous, almost like depending on what you mean, whether something halts, right? Here's a great example of one that we provably know can't halt. Give me the prime number larger, the next prime number after the largest known prime number. We don't know if there is one of those, right? We don't know if there's an infinite number of primes. We only know what the largest prime number is. And so you can ask a computer to start computing that, and what's it going to do? Well, it's going to try the next number, then the next number, then the next number. If we could prove that it would halt, then we could prove that there are an infinite number of primes or not. And we know we can't do that because we can't even factor numbers, right? So there's these tasks around that they have to be the case that we don't know they can halt, because if they could halt, we would be able to infer things about the natural world that we haven't been able to determine, right? So there has to be some things that computers can't solve, and the things that computers can't solve, they don't halt on. So the halting problem is the notion of things computers can't answer. The plan is we are going to address the halting problem in the lecture I'm going to record on Monday for you to watch when you get home. That's the plan. So it'll be swirling around, and then we'll approach it scientifically at some point in the future. We have to build up a little bit more technology to understand it first. So in general, we like our Turing machines when they halt, and they halt over nice problems, and they don't halt over nasty, challenging problems, but they don't halt over interesting problems, right? So a Turing machine M halts by entering Q accept or Q reject, but we cannot compel it to forcibly enter one of those states after some point. Now we can do some things, like we can say, this Turing machine is going to maintain an internal counter, and after it has taken 1 quintillion steps, it will enter reject if it has not entered accept yet, right? But, as with all of the other examples, you don't know if it was 1 step away from entering accept. So that still doesn't tell you anything about the problem, right? Modern computers often have these execution monitors that turn off computation after a certain amount of time to prevent infinite loops, right? And we essentially only encounter infinite loops in programming languages now, where we have been trusted by the computer to know what we're doing. Because one example of an infinite loop is a web server, and that is supposed to be looping infinitely, right? But most programs that are, I think, distributed to consumers have execution monitors so that if someone accidentally enters an infinite loop, it shuts itself off after some time, right? And it's not that hard to implement something like that. So what this means is that versus a finite automata and a push-down automata, those things return 0 or 1. Turing machines do not. They return 0 or 1, or they don't return. So they may return 0 or 1. The thing they return is in the set 0, 1, but it might also return nothing. And so that's the difference. It's not too bad at all between true, false, and you see why we have none in Python. It's this thing that's not quite false, right? Here's a statement that doesn't return anything. And here's a statement that does return something. We regard these as quite equivalent. Because I think that returns none. What is that? If I cast this to a Boolean. There. So none and false are similar in Python. There's no real notion of none in some languages. One of the early languages, Lisp, had something called options, where you could specify if it was possible something would be none or not. And it imposes considerable computational overhead, right? So every single thing in Python has to not just carry around its own value, but also a sign that says, I am not none. And on modern computers, this isn't a problem. On early computers, you see it was a big deal. So Turing machines can return 0, 1, or nothing. And nothing and 0 are not the same thing. We should think of this in our minds as very similar to the notion that the empty string and the empty language are different. The empty language is the absence of a string. The empty string is the absence of a character within a string. Okay. We accept a word by halting in QAC, QAccept, and we reject a word by halting in QReject, and we also reject by not returning. Just keep spinning forever. Right? Is this deterministic or not?
It is deterministic.
Yes, it is. And what makes it deterministic?
Because there's only 3 outcomes over there.
And this thing here always goes to a fixed state, right?
Fixed state.
So you're going to proceed deterministically through a sequence of states based on the letters you're provided. You will always get the same answer. Some machine learning researchers have been tempted to claim that elements of machine learning are not Turing complete because they are non-deterministic. That's a very, very strong claim, right? I think it doesn't look deterministic to us because there's big numbers in it. It is a very different claim than this is actually, solving some problem that a Turing machine can't solve, right? I think machine learning is actually the solution to the problem of it would be hard for me to write this program myself, not this is a program that a Turing machine could not process, right? Because the machine learning networks are all running on Turing machines in some abstract way, right? If we wanted to make this non-deterministic, we simply throw power sets in there somewhere and we'll figure out where the power sets go later, right? All right. There's a difference between recognition and decision. And we need to introduce this because this notion of halting is going to sort of be clawing at the back of our consciousness. It's going to pose real problems for us. It causes many open problems in computer science. One of my favorite results is Nancy Lynch's paper on the impossibility of distributed consensus, where she proves that 2 systems connected over a network can never actually agree on anything. And you can prove this. And that's kind of a big deal for the internet, where we sort of all think that we're looking at the same web pages, and in practice we tend to be. But even just here, so on these slides that are obnoxiously hosted on the internet by a web server I have to maintain myself, right? Frequently I got them to look different on my local device and thought I uploaded those devices to the computer, and in fact there's some disagreement between consistency between them, right? And In this case, it's user error, but I also understand there's an underlying problem that is very, very hard there. Like GitHub or just Git version control is fundamentally trying to solve an impossible problem because you just cannot fundamentally answer, what if some remote computer appears to be in the process of a commit, that computer crashes, and the last bits it sent looked like the beginning of an end of file character. You don't know if you actually got that whole message or not. There is no way to determine if you actually got that whole message or not. That means Git version control can never halt unless it allows itself to potentially be wrong, right? So you have to gamble, or you have to guess, or you have to make an assumption that could be incorrect. And it could be the case that two different computers disagree on the contents of a GitHub repository. That has to be allowed, it provably has to be allowed. And we're going to think of this in the terms of notion of recognition and decidability. So we're going to introduce the term Turing recognizable. We have introduced automata as things that can recognize languages. No problem, we're going to let M be a Turing machine. It is dramatically more powerful than our previous M's because it can read and write, has random access memory, it can go left and right, it can deal with infinite tapes. Massively more powerful than a push-down automata. Simply enough, we say the language of M is the set of words, or strings, or what have you, right? A word is just a sequence of strings, such that the machine, when it reads W, enters the accept state. That is all. We say M recognizes L if the language of M is, or M recognizes L, M recognizes A, blah, blah, blah. If the language of M is equivalent to A. Okay. Turing recognizable means, well, okay, let's take a step back. Turing recognizability is a property or an attribute of a language. A language can be Turing recognizable. Here's an example of a Turing recognizable language, the language that contains only zeros. This happens to also be a regular language and a context-free language, but it is also a Turing recognizable language. Any language is Turing recognizable if there exists some machine that recognizes that language. The example of the non-Turing recognizable language is the language that only returns the largest prime number. We have no idea, right? But we can write a Turing recognizable language that recognizes any prime number, right? Decider is a much, much stronger claim. A deciding Turing machine, so this just means it accepts things, right? This doesn't mean that it never fails to halt, right? Decidability is more useful to us because this means that on all words, no matter what I give my Turing machine, I am guaranteed that it enters either accept or reject, which means this is essentially real-time computing. This is the type of computing you have to do in spaceships and cars and nuclear power plants and things of this nature, because you can never start evaluating a sentence and not know if it's going to come back before you have to drop the cooling rods, or before you have to depress the brakes, or before you have to lift off of your launch pad, or whatever it is you're doing in real life, right? Decidability is much, much stronger. The problems that can be solved by deciding machines are much, much weaker and much less interesting, but they are very, very important. And an interesting theoretical problem in my first job before I went to grad school was to essentially write real-time code that never did anything that was undecidable, but still did interesting things, right? So we say M decides A, not recognizes A, decides, a stronger claim, if the language of M is A, and also M always halts. For all input strings, it enters accept or reject. Under no circumstances does it fail to halt. There exist things that are recognizable but not decidable. And many of these are interesting, right? So we have this new series of sets and subsets, and I view this as sort of the universe of languages. There are potentially super Turing languages. It's unclear if those are academically interesting, or it's unclear if as soon as you get past Turing recognizable, you just go to the universal set, right? So we have regular, which is very restrictive, context-free, which is less restrictive. We know there's that one thing between regular and context-free, which is whatever is recognized by deterministic push-down automata, and no one cares about those at all, right? But there are intermediate categories we have papered over, right? From context-free, you go up to Turing decidable. Turing decidable is very academically interesting to us because that's what we can do in real-time contexts. Linux is now a real-time operating system, so it is possible to write an operating system that is decidable, right? And then we have Turing recognizable, that's things like the climate models, protein folding problems, all of the LLM models. We don't know if those things are ever going to return, but they do with high probability, and we just turn off the computer if they don't, right? So there's this Turing recognizability that's extended out there. I'm going to furnish you with some slight additional terminology. I do still never love using people's names to describe things because it seems odd to me. So I'm going to give you two other terms, and I'm never going to use them again in this class, but I'm going to let you know they exist in case you need them. A recursively enumerable language is what the linguists were calling the languages that are now known to be Turing recognizable, and they are stronger, slightly stronger, than recursive languages, which are those that are Turing decidable. And I am not super good at differentiating these languages. I had a class on them. I did not do well on the midterm where I was supposed to tell these apart. It doesn't help me that they contain the same word, like recursive language and recursive enumerable language. It's like, whatever. So I think it's much easier to remember one of them relates to the Turing machines that halt and not. I'm much more experienced with real time than I was then. You are probably not experienced with real time, so you don't have that benefit, right? But you can always refer to these things as recursive languages and recursively enumerable languages. RE is very common for recursively enumerable language. The same way we'll just say CF for context-free, we'll say RE for recursively enumerable. And so here's another way to look at this. Recursively enumerable, recursive, context-free, regular. And with that, we have to take a stretch break. I'm due for a bathroom break, so I'll be back from that after. And what are we doing next? I think we're doing Turing machine variants, right? Yes. Time check. I will let you ask me questions when I get back, but I'm not going to accept questions at this time. We're back on schedule. Okay. I'll just keep talking faster and faster. What's a Turing machine?
Sorry?
What's a Turing machine?
Turing machine?
Yeah, what is it? What's a tape?
Tape is a stake. Stake of.
How long is a tape? TAPE.
How long is a tape?
How long are they?
They're just long. Then we can't measure them.
Yeah, arbitrarily long.
Arbitrarily long. They're just long enough.
Yep, always long enough.
Always
Right.
long.
Yeah, so they're not long enough to write a real number on,
Yeah.
but they are long enough to write a natural number on. And somehow those are different lengths. What's the difference between sigma and gamma?
Sigma and gamma.
Yeah, big sigma and big gamma are two of the 6 elements of the 6 tuple that forms a Turing machine. The first one of them is sigma. What does sigma represent?
Sigma represents the value in the state, right? Like, and the gamma is basically the state.
Okay. Do they appear inside the Turing machine or on the tape? So if a Turing machine is reading and writing from a tape, where is gamma? Is it on the tape or is it inside the Turing machine?
Sigma is on the tape,
Sigma's on the tape, yep. And
and the gamma is on the Turing meter because it's a variable.
yes, okay, that's good. Gamma is inside of push-down automatas, and it is outside of Turing machines.
Outside of Turing machine.
And the reason for that is Turing machines, essentially the gamma, essentially the push-down automata stack is the Turing machine tape, because it can just write its stack onto the tape. So that means that in, like, for example, the context-free languages, which have the variables and terminals, as you mentioned, right? Those are different things in the context-free grammar. In Turing machine, it just writes everything on the tape. Everything's on the tape.
Everything
right?
is on the table.
And what that means is when it enters Q accept, it must have gotten rid of all of the things in gamma that aren't also in sigma. Okay, what does it mean to halt? H-A-L-T.
Give me a minute to.
I'm going to review my slides here real quick anyways. Visual things that look good here. Wow, there's like no pictures left. Oh, this one's good. That'll be a good one to take a picture of. Okay, I'm going to turn on this other one. I don't know if this thing actually.
Oh, I get it.
Okay, let's halt it.
Halting is the process of acceptance states and rejection states. It's where to stop, where to start. That process called halting. Yeah.
Yes. Essentially, it is the union
It's like loop.
of halt, except, yeah. And then, yeah, it's the negation of loop. Okay. All right. So when we get to slide 13, we're going to stop and we're going to draw part of it on the board. And we're going to stage this cup somewhere. And I'll put on this name tag. And then we'll look like we're at Lagrange. Okay, we have to figure out some way to take the picture that we're both in, but we can probably do that with the webcam if necessary. Cool.
Get place. timer on the front.
Yeah. Okay. Cool. All right. So, basically, the very first thing we did when we started dealing with finite automata is we tried to write one proof. And it was absolutely miserable. We're like, wow, this is so complicated. We have to keep track of a bunch of deltas and everything. And so then we came up with this other idea. If we're going to write miserable proofs anyways, why don't we give ourselves non-determinism, which is a bazillion times powerful than the next most powerful thing. And then we're like, well, why don't we also just change our edge labels so they can just be entire regular languages? And then we had generalized non-deterministic finite automata, and every proof was massively easier, right? And it wasn't necessarily easy to write the proofs to use that stuff, but as far as proof techniques go, then we could suddenly say, oh yeah, these definitely are the same thing as regular languages, right? So the first thing you do with Turing machines is you take a look at your Turing machines and you say, gosh, I really don't want to write a program that runs on a Turing machine. It would be really nice if I could have non-determinism, more than one tape, large numbers of languages, maybe I can throw a stack in there or something. And in fact, we're going to do all of that. So when I put variants up here, the first thing I learned when it came to Turing Machine, I think, in my case, I think I wrote like, my professor had me write like one proof with a Turing Machine and say, wasn't that awful? Okay, let's prove that you can use more than one tape. And it's not too bad to use more than one tape, and it's not too bad to implement non-determinism. The performance goes down. And since we're relying on our hot Silicon Valley startup writing a really, really fast Turing machine, we're allowed to have bad performance as long as we haul. So we're going to dramatically increase our computational power before we start doing any really interesting proofs on these things, right? So we're going to refresh what Turing machines are, then we're going to build a multiple tape Turing machine, and then we're going to build a non-deterministic Turing machine. And then we're able to actually do things that are interesting with Turing machines, right? As with the closure properties, of course, as we're doing later proofs, you'll realize, oh, I could do this on a deterministic Turing machine. And the way you would do it is you essentially do exactly what a multiple tape Turing machine does anyways, right? The multiple tape Turing machine is like so easy for me to understand, because I remember one of the first things I did with computers when I was younger is in those days, people's hard drives were always filling up because they were small. They were like 30 gigabyte hard drives or something, and an operating system was 8 gigabytes. And then you download one movie, and it's like your entire hard drive, right? So it was very common for people to have external hard drives. So it was very obvious to me that I could plug 2 hard drives into one CPU and write to both of them at the same time. There was no law against doing that, right? And so as soon as I heard of Turing machines, I was like, well, what's preventing this thing from having 2 heads? Yeah, I mean, it seems like it should have a very, very large number of places it can write memory to, right? So why are we going to use this model? Blah, blah, blah. Okay, back to defending Turing machines. So I'll reiterate this. All of the models are equivalent in power, and by all models, I mean Gödel's general recursion, Alonzo-Church's lambda calculus, Post's machine, and Turing's machine. And maybe there's one other one. Oh, the recursively enumerable and recursive languages. All of these things. I believe 12 years ago I saw a recursively enumerable language written out, and I don't even remember how I'd write it out, right? It's just Turing machines all the way down. And I write a little bit of lambda calculus just for me. In a way, this thing is more like JavaScript than anything else, where it's like everyone just started writing JavaScript at some point because it ran in web browsers, and now 70% of the code that's written every day is written in JavaScript, and no one thinks JavaScript's a particularly good language, but it's certainly good enough. I have a tendency to go to Python, as you've seen, where I just pop open Python and start writing it. But I teach in another master's program, and I walk around the class, and 70% of them are writing in JavaScript because it's just the language they think in. There's nothing wrong with that. My impression is that's actually very close to what happened with the Turing machine. It was there, it was good enough, there was no reason to iterate over it, and now it's an accepted standard. To make a language that's enough better than JavaScript, everyone would change how browsers are implemented, is never going to happen. And to make a model enough better than the Turing machine that every single theory of computing result is regenerated, it's just never going to happen. It doesn't make sense. The Turing machines are easy enough to work with. So everyone in the world is going to use Turing machines until the end of time. The thing that would probably challenge Turing machines is like the emergence of the quantum computing paradigm or something, right? And of course you don't use Turing machines for that. But in fact, probably people will use non-deterministic Turing machines for them, which we're going to prove are equivalent, right? So separately, it has been articulated to me that students, which tend to be third, fourth year undergraduates, first, second year graduates, they seem to do best with Turing machines. So I'm doing it for you. And I do much better with multi-tape than I do with single tape, right? So what's going on? We just finished looking at a push-down automata, which was able to write and read to two places at the same time. And we said Turing machines are smarter than push-down automata. So why can't a Turing machine read and write to two places at the same time? Well, regardless of whether it can physically do that or not, if I actually had a physical Turing machine sitting in front of us, I can program a Turing machine to do that. And I can program it to pretend it's a multi-tape Turing machine. On this computer, I showed it to you earlier, I just opened up Linux and ran Linux in a virtual machine on my computer. Turing machines can also run virtual machines. And a single-tape Turing machine can run a virtual machine of a multi-tape Turing machine. And it can run, for example, a virtual machine of a single-tape Turing machine with a stack. And it would do that in the same way, right? So how are we going to do that? Turing machines can read and write. They can do the thing that you used the stack for. We're just going to read and write to different places on the same tape, and we're going to pretend that they're different places. I forgot. I wrote these slides on a desktop device that has both a solid-state drive and a hard disk drive in it, and now I'm presenting it from a laptop. This device does not have a hard drive in it. It would be twice as big. This has absolutely nothing in it. It has a very tiny solid-state drive that is very hot. So here's the minimal model. I'm going to take a Turing machine. Any Turing machine will do. This Turing machine has all of the things we expect a Turing machine to have, which means it has a finite number of states, a finite number of output symbols, a finite number of input symbols that is a strict superset, that is simply a superset of the input symbols. It is going to have some delta function. What is the delta function? That's the actual computation. That's when it looks at a letter, and it looks at its current state, and it determines what its new state is, what its new letter is, the new letter it's going to print, and whether it goes to the left or to the right. And then there's going to be an initial state that it thinks of when it starts, then there's going to be an acceptance state that it might think of when it completes, and there's going to be a reject state it thinks of when it completes. And perhaps it will never get to the accept and reject state, we don't care. But that is all of the things a Turing machine has. Now, what is important to note about this is when I described the delta function, I said, it reads exactly one letter. But there's no reason it can't read a billion letters, or any finite number of letters at a time, all potentially on different tapes. So we're going to add any number n of work tapes, including a billion. The first time I wrote this proof, I wrote it for n of 2 specifically. We just added a second tape, and then we say by induction you have as many as you want. There's not actually a particularly compelling reason to do that, because we're not going to use 2 anywhere in this proof. Right? We're going to call these things work tapes. We just have to call them something. And we do want to differentiate them from the main input-output tape. Here's an example of this. When I work in Python, I open the Python script, and it reads and writes to standard I/O, to standard input-output, directly at the terminal, right? But I always have access to a little work tape I call the file system. I can open and read from a file, and I can open and write to a file at any time. I can think of that as just being the same thing as a second tape, right? That file can be saved to a solid-state drive, or it can be saved to a hard drive. And in most modern programming languages, especially something like JavaScript, I can read and write to a network location, right? So I can write anywhere on Earth. And in fact, in Python or any other language, I can create multiple threads that write to multiple different files at the same time, and none of these things are more complicated than just running serially very fast, right? So, I'm going to imagine I have multiple work tapes, but they are all different than standard input-output. And then I can read and write to any of them. It is also going to have a head position on every tape. This is not that complicated either, right? So, do you use Vim, V-I-M, the text-based text editor? Have you seen this thing? Yeah, you do. Well, someday it'll get you. I resisted for many years, and I've succumbed recently. I started using Vim. And the problem with using Vim is, right, it becomes your whole personality. And, yeah, you see the problem I've gotten myself into. If I open 2 files in Vim, and I navigate to 2 positions in the file, and I close both of the files, then I open them up again, Vim puts the cursor exactly where I left it. How does it do that? It's not particularly complicated. Vim writes to a little hidden file, and the only thing it writes in that file is how many bytes I am in each file. That's all it is, a very, very tiny amount of information it has to keep track of. And remember, I have a very big infinite tape. So it is simple to imagine if a modern computer can use just a tiny number of bits to keep track of where I am in a file. Of course a Turing machine can do that in the same way, because a Turing machine can write to a tape. And so it is not that hard to imagine that I have different head positions being tracked on different tapes, because on my computer I have different head positions being tracked in different files all the time, and then it is very easy to imagine how useful this would be, right? Even just now, so if I press Alt-Tab, this has persisted my history. I did not start back at the beginning of whatever is in this shell script, right? I'm not all the way back up here with whatever this is, which is apparently blank, right? Modern computers do this no problem. If I tab over to my web browser, we'll see that the most recent scroll level is kept track here. I'm causing recursion right here, so I'm going to close this room. Okay, got to watch out for those recursively enumerable live streams, right? They might never halt. Okay, so we're going to maintain its position on all tapes. Okay, we are going to claim, and we're going to formulate this in a, I don't know, a way familiar to us because we did 12.5 contact hours of automata theory. We're going to say a language A is Turing recognizable. We're going to say if and only if, but we can just do the two ifs separately. Are you familiar with the term if and only if, the IFF? Have you seen that before? Yeah, just bidirectional implication, by implication, right? If some multi-tape Turing machine recognizes A. So what is that? Well, something is Turing recognizable if it's recognized by a single tape Turing machine. So if we have a proof that we can recognize anything that is recognized with a multi-tape Turing machine, there we have it. Okay, so how are we going to do this? We point out that one of these directions in the by implication is quite simple. If I wish to pretend that I can emulate a multi-tape Turing machine, or a single tape Turing machine on a multi-tape Turing machine, that is very easy. I simply never write to any tape except one. Very easy to emulate a single tape. You just leave the work tapes blank, you never move the head, you don't read, you don't write, you don't do anything. You simply restrict your delta so that nothing happens on any of the other tapes, right? Very easy. Not quite so easy to go the other direction, but not so bad either. So what are we going to do? Well, let's take two Turing machines. We're going to call them S for the single tape Turing machine and M for the multi-tape Turing machine. I didn't love writing it this way because I've been using M for machine for a while, so with apologies for if that seems confusing, right? And S stands for simulant.
Single M stands for multiple.
Yeah.
Multi-tape.
Yeah, I guess maybe I should have called it N for like some arbitrary N. I did, right?
It's fine.
Yeah, we got it. Okay, so
easy to determine M for multi and S for single. So
if you say so, I believe you. Okay, S is going to simulate M. How's it going to do that? Well, all of those work tapes are potentially infinite in size, or well, they're uncapped in size. They're arbitrarily large. But arbitrarily large times any finite number is still only arbitrarily large. So I'm simply going to take all of the things that M was writing onto its multiple tapes, and I'm going to write it all onto a single tape, as if in an array. I'm going to write a tape array to my single tape, because I have infinite tape in any direction. So if I have simply one other tape, no problem. I take that tape and I write it at the end of my previous tape. And you say, there is no end to your previous tape. Oh, then I write it at the beginning, and I grow in the other direction. No problem. So I'm going to have blocks. And you will recall not too long ago, I told you that cloud architecture, to my knowledge, is optimized for solid-state disk reads of block size. This is just, in fact, how physical hardware works. It works in big blocks. A file is very, very close to a tape of a Turing machine, and in fact, a file is much closer to the tape of a Turing machine than a hard drive is. Right. We're going to introduce one symbol. I'm allowed to use any finite number of alphabet symbols, which means I can always add one symbol. So I'm going to add one symbol, and I'm going to call it the tape break symbol. This is the special symbol that is only used in between tapes. The tapes already have their sigma and their gamma, and I'm going to add one thing to just gamma, right? Because I'm going to delete it before I return. And it is going to say, this is the end of one tape and the beginning of another. This is virtually identical to end of file. This symbol actually exists in physical computing devices, right? This is the end of file symbol. It is used everywhere. Every file on my computer knows where it's ended because there's a special character at the end of the file, and that's that. It's Control-Z, you know. These things are around. They exist in computing devices. They were implemented. We're going to add one additional symbol as well. It's going to say, this is where the head of the Turing machine is. There's other ways to do this. So if I were writing this proof, and I followed Professor Sipser's very carefully, I would not have done it this way. I would have had introduced two new symbols. One of them would be tape break, and one of them would be end of prefix. And the end of prefix symbol would come after the address of the head. So I would say where the head is by address. This is what Vim does. That's what I was thinking of it doing. Professor Sipser does this very interesting idea instead, where he says, well, I can actually just double the number of characters in the alphabet. And so that for every character in the alphabet, I also have a copy that says, not only is this character at this location, but also the Turing machine head is at this location. And then what you do is you just read along one of your tape blocks until you see the one that says, this is where you left the head. You erase that character, you write the character that says the head isn't here, you do your computations, then you write that character back, and then you leave to another tape when you're done computing on that tape. So logically identical. And then in my variant, the only difference is when I run back to the beginning of the tape, I have to write my address. So I have to have some internal counter, right? Managing internal counters is pretty hard without having multiple tapes, so that's a compelling reason to use this alphabet, right? So here's the statement of the proof. We're going to have a single tape and an M multi-tape. We're going to simulate. We're going to have the tape break symbol. And here is how this is going to work graphically. So I have denoted we have 3 tapes here. We're going to consider a 3-tape model. I wanted to give you more than 2, because I did this with 2, and then you have to write sort of essentially another step to go past 2. So one of them, and I've even given them different languages, which you don't have to do. So the sigma for this whole thing is perhaps these are the only terminals, perhaps these are the only terminals. It doesn't matter. All of these things are in gamma somehow, and some of them are in sigma. I am using now underscore as the blank character instead of 0, and I'm mostly doing that for visual clarity. You always get to decide what you use as your blank character. The other thing I was thinking of putting here was the null set symbol. But they're not sets, right? This is the absence of anything, right? So here are my 3 tapes, A, BB, 101, CCC, A. I use the octothorpe or the hashtag or the pound sign as my tape break symbol. And so my single, my Turing machine S writes AAAB, B, octothorpe, 101, octothorpe, CCC, A, blank. You should be very nervous right now, because you should ask me what happens if I have to write a character here. And something very annoying happens. And if you've used low-level programming language, you realize this is what happens, which you have to take all of these characters and you have to copy them further down.
How?
Well, if my Turing machine is computing and it realizes it needs to write something and it reads an octothorpe there, I have to program my Turing machine so that before writing that thing, it goes all the way to the next blank, which is here. It goes back 1 to the character before the blank, copies that character to here.
Oh.
And then it repeats that, and it has to move all of these down one at a time.
It will move all the characters from...
It moves all the characters one at a time, yes. And you're thinking, can't it move them 7 characters at a time? And it's like, good luck writing that, right? It's much easier to write the move 1 at a time, right? And fortunately, I have a hot startup coming out of Silicon Valley that has the move character 7 at a time thing. That's something that I can fix with engineering, right? So we're allowed to just assume we have to move 1 of them at a time. And it's very painful to us, but we realize, ooh, that would be annoying to write the program, but it's very easy to say the proof that I do that, right? I just say, oh yes, I copy all of them down 1. trust me, you know. And then the only thing you really have to worry about then is, oh, you have to remember what character you were going to write here. That's not too hard. Put an end of tape right here, put the character you were going to write right here, copy everything down, go to the end, copy it back. So you can always use workspace off the end of the file. So this is essentially, I don't know if you've ever implemented like a linear probing hash table. Ooh, I had a hash collision. I need to find some working memory off somewhere in Narnia and then expand the size of my tape. And so none of that's too complicated to work with, but it is a little bit tedious, and we should understand that when a single tape Turing machine is simulating a multi-tape Turing machine, it is going to have ludicrously poor performance, in the sense that every instruction costs any finite number of instructions, right? So this can be a slowdown of any arbitrarily high speed, right? So it can be 1 billion times slower, and it can be 1 billion times slower per tape, and I can have 1 billion tapes, right? The only thing we're showing is that it's possible. Okay, I think this is the one we should take a picture of. We have our head, and in the multi-tape machine, we've been considering that we have a different head on each tape. Why not? And so the head that points to the 1th tape, which is denoted with a 1, or the first tape, is pointing to the first B. The head 2 is pointing to the first 0, and the head 3 is pointing to the first C. Our simulating machine, S, the single tape machine, only has 1 head. So it somehow has to track all of this additional information. And in addition to doing all of that, it has to do things like copy this tape down if there's a problem, which means it might have to store the position of all of the heads at the same time, and then go do some maintenance tasks, and then come back and pretending to be simulating again. So we're going to solve that with these special little characters that you can't even see, but we extend our character alphabet, and that's how we can simulate the head. Okay, let's go draw this on the board. I'm going to make you draw a multi-tape Turing machine. How's that sound?
Okay.
All right. What is a multi-tape Turing machine going to be? Or I'm going to ask you to draw S that corresponds to a multi-tape Turing machine. How big is the tuple going to be?
7.
Oh, is it 7? It might be 7. I don't know for sure. I thought it was 6, but 7's fine. Okay, what is one of the things in the tuple?
Sigma.
Awesome, yeah.
Delta.
Nice.
And stake. It's gamma.
Gamma, yep.
Starting stage, initial
Yep,
stage.
yeah.
Acceptance.
Yep.
Initial acceptance stage.
I think you said initial state and acceptance state. I have 5, and the one you're missing is reject, by my count. The rejecting state.
Rejecting state.
Yeah. And I think that's all 6. Okay. All right, go write that down on the board. This is your first homework assignment. Or it's actually your second homework assignment. I made you do something yesterday, right? Okay. Right. Accept. Okay. Do you want to take a picture of us with me writing or of us with you writing? All right. You have a timer on your phone? Let's stage something. I have to hold this cup.
307.
Okay. How do you want to do a picture? I think we have to photograph us. Are you still up for that?
Yeah.
Okay. what I was thinking would be cool for you to do is I was going to ask you what sigma is for this setup. And so I was going to ask you to populate this with the elements of the setup, or gamma. And I will stand here and help you, and we'll take a picture of both of us somehow. Should we use my webcam? I'm thinking I can put my computer there and take a picture of us on our webcam and then screen cap it. Do you have a good way to take pictures with your phone instead?
The phone camera is better than the webcam.
Yeah.
You have the better quality. You can
Okay, cool. I'll stand here and set up the shot, and then you can come take a picture of us, or however we can do that. Does that work? Cool. You ready?
Or we can stage it like first I will take a photo,
Mm-hmm.
and then I will come over there. We
Okay.
can.
I want both of us together because I think
I can.
you
We
use
can
my-
do that thing.
Okay, cool.
And we have a feature in my phone.
Yeah. Okay.
First, I will take your picture. I'll show you.
Okay, well, we'll just simulate it.
Let's just simulate.
Okay. So take a picture when I look convincing. Okay, so we have.
Okay.
Okay, you got it?
Yeah.
Cool.
Now what? I will be there.
Yeah. Okay. And I have to stand in roughly the same place.
Yes.
So you were here. Cool.
So I don't have to be. I will just watching it like this.
Okay. Cool.
You don't
move
adjust the
camera
frame
forward.
to.
There we go. Cool. Let's check out the group photo. That's really cool. All right, that's great. Thank you. I'd appreciate it if you send that to me, and if you don't want to send it to me, then don't.
No, never mind.
Okay, thanks.
I'll send it to you.
Very cool. That's a nice feature. That's like a non-evil use of AI, right? Like, oh, we don't have someone to take our picture.
But you can't share the difference. It's
Yeah.
right.
Yeah, it looks good. But like, it looks good enough. I think you can like tell it's fake a little bit around like some of the artifacting under the reflection and stuff, but it's not bad at all. Cool.
I texted you this picture.
Thank you so much. Oh, I probably got it. Okay. So, just looking over there, because I was writing things down, I started writing things down in gamma. What is an example of one other symbol that goes in gamma?
R.
Why does R go in
Small r.
gamma? Why does small r go in gamma?
This.
What does small r represent to you? Or perhaps, what is gamma?
Gamma is a stake of values.
Yeah. So I call it we called it the stack alphabet, right? And then now we're using it for, now it's the input alphabet, right? So everything that can possibly be on a tape is in gamma. Is R on any of our tapes?
No, I guess.
Yeah. The first three characters I have up over there, I'll show you how I found them. I did A, and then I did B, and I was actually just looking up here. I did A and then I was B, and then I noticed that I have to have this special version of A and B that denote the head is in that position. So I wrote A with a little dot on top of it. So these are all characters that could possibly appear on this tape here, right? What is another character besides those three that could appear on the tape for the single tape Turing machine?
I guess it will be Q0 because we have the head starting point, right?
where do you see Q0 on this tape?
I referring like to starting point, initial point, head. Head could be Q0, right?
Yes, the state of the head could be Q0, but gamma does not represent the state of the head. It represents the letters on the tape. So this is the difference between Q and sigma in a finite automata. This is the difference between Q, sigma, and gamma in a pushdown automata. This is the difference between... Those are the only real differences, because this is an automata difference. The internal state of the automata has absolutely no relation, no correlation, no correspondence, nothing in common with the letters that are written on the tape, right? It is the difference between how I imagine a character in a book I read and how the character is described on the page. They are related to each other, but one of them is ink on paper and one of them is neurological, right? Gamma most closely corresponds to things I have written down on the page. You'll see some of the early examples are A and B. When we denote the state of internal Turing machine, we often just refer to them by some symbol as well, but they have nothing in common. So with those motivating remarks, with the notion that gamma is the alphabet of the tape, or the input alphabet we also call it, which is the combination of the stack and the output alphabet for the pushdown automata, which is the combination of the variables and the terminals for a context-free grammar. What is another symbol that is part of the input alphabet of the tape? And three examples are A, B, and A with an accent over it. I guess I could say A, B, and A. What else do you see on the tape?
I see in the tape. I guess there is no rejection point in the tape, right?
The rejection point is a state, and it is not the same as the tape alphabet, right? The states and the tape letters have no relation.
Have no relation.
Yeah.
So Q. I think sigma is over there because no.
So A, B, and A prime are perhaps members of sigma.
Members of sigma.
Yes, they're elements of sigma, I guess I would say. What is another element of sigma? Besides A, B, and A. I like saying that. That's fun.
Lowercase sigma.
What would lowercase sigma represent? I don't know what you mean by that.
No.
Yeah.
I was just guessing.
Yeah. So on this image, where do you see A and B? And perhaps A. A.
We have A over there.
Yeah, here's an A. There's a variety of A's, right?
Yes.
Okay.
We got B.
Yeah, we got B. We have a variety of
But
B's.
we don't have A with...
There's no A on this, but there could be, right?
It could be.
If the head was, if H1 was here, right? Instead of being A, this would be A. So what's another letter we see on this tape that represents gamma? It is represented by the letters of gamma, right?
I think pound.
Pound? That's a great choice, right? I called this the special tape break character, right? And that's a great example of something that is specifically part of gamma and not part of sigma, because we're going to erase it before we return, right? So gamma, the input alphabet, is represented by all of the letters that could possibly be on this tape, and specifically those letters. It does not have any bearing on which of those letters persist on the tape after we return. It does not have any bearing on which of those letters come from one of these tapes. And it has nothing to do with what is in the finite control in the box that represents where the head is and so on, right? So gamma to me is A, B, the tape break character, 0 and 1, with and without accents, and then also C, with and without accents, right? And perhaps there are more letters here, right? And of those, I expect the tape break character and all of the accented characters are part of gamma, but not part of sigma, because the tape break character and the accented characters are only used by S to simulate the multi-tape machine. So they should not be visible to the end user. In the same way, any sort of internal implementation I do in my program should not be visible to the end user. So I should not expose an API key to my end user. I should similarly not expose a tape break character to my end user. There's a famous XKCD. You have to be careful about naming people end quote, end paren, semicolon, drop table, because that's an SQL injection attack, right? So this should never be returned to the end user. This should never be returned to the end user. So it is part of gamma and not part of sigma. It's another example. Like for a programming language, this is not part of sigma.
Comments.
We don't pass the comments to Python. Doesn't care. It says I'm busy, I can't read that right now, right? And I think that's one of the reasons why the octothorpe to me felt like a natural character for a tape break. Because in fact, what I could do, and I would never encourage you to do this, right? Wait, no, is it console? Yeah, I think it's console.log. We could do something that's very silly, which is we could write JavaScript inside Python, right? And we simply put it in a comment, and we say, dear Python, copy this to a JavaScript file, right? Do I have Node on here? Okay. One of the examples I do in another class, and it's not particularly relevant here, is you run JavaScript inside of Python with os.system, and you say, look, this is runnable Python code. It's a string that contains JavaScript, right? But I recently wrote a Python program that contained the text of a C file. It wrote the C file to the file system, compiled the C file, ran the C file, returned the results of the C file, deleted the C file, deleted the executable, and then of course it can even delete itself, right? And so it's like, look, Python that runs C. It's so fast, right? It makes a lot of sense to do this with JavaScript. It's like, look, I wrote Python that can run in the browser. It does so by opening the browser, running JavaScript, right? Okay, how do we deal with this in practice? Well, this is heinously painful to deal with, because when we were dealing with the push-down automata, how many times did I say, I look at the stack, I look at the tape, if they're the same, I make some decision? Well, that's not super easy to do now, but it's still possible. And the manner in which it's possible, oh my gosh, I have a lot of hair. The manner in which it's possible is I go all the way to the leftmost, the same way we did with our first Turing Machine example, and I read all the way to rightmost, and I just look at all of the symbols that currently have the head at them. And then when I get to the end of rightmost, I make my decision based on what my internal state is. Then I go back to leftmost, and I update everything, right? And so if I were to be emulating a push-down automata, read the whole thing, see where the heads are pointed, and then when I get to the end, I say, I entered a special state if the heads were of the same value. Then I say, perfect. Then I scroll back to the beginning, then I delete both of the heads, then I set the head in the next position. And so you're running back and forth across it a lot. This to me is not that unfamiliar, because if you've seen what are the seismographs? These things, they go back and forth all the time, right? So to me, when I first heard, you just have to read every single character before you write a single character, I was like, oh, I mean, that's slow and low performance from a performance engineering perspective, but in terms of an actually physically existing device, that's not that hard to imagine. I need to time check what time it is, 3:21, okay. So we're gonna maintain the head location on each tape, okay? You have to do this copy thing. Probably the natural way to handle this is that actually every time you hit the end of a tape, you create a special not quite blank symbol and you double the amount of working space each tape has. That's performance engineering on a Turing machine. Don't do that. Just say we copy it every time we run out of space, right? Yeah, this is in fact identical to how Python does lists though, right? So when you create a Python list, it gives you 2.7 times as much space as you need and just hopes that that's the right amount. And so on average, it wastes half the space. Okay, here's our proof. And I say the proof is just the extended alphabet and the tape break characters. And I say that's a sufficient proof, right? It is a simple enough matter to show that you can serialize any multi-core program. It's just low performance. Non-determinism is the next thing. Okay, that says 323. Okay. Definition. A non-deterministic Turing machine is the same 7-tuple. See, here I'm saying it's 7. I don't know if it's 6 or 7. I can't count that high.
We counted 6.
I can't count that high. I have no idea, right? We're going to update our transition relation. So remember this transition relation. What do? I'm thinking a thought. I'm reading a character. To me, it seems like one of your common sources of confusion is conflating states and characters. Don't do that. They're different. There's the thought I'm thinking, and there's the text I'm reading. There is what I think the Python program is going to do, and there's what the Python program does. There is the thoughts I am trying to express in the email, and there's the actual physical text I write in the email. I think emojis are actually very interesting for that. I'm never thinking like this face, like, but like sometimes I send an emoji that looks a lot like that, right? So that's the difference there. There's the way we encode the information, and then there's separately the internal state of the Turing machine and what its process is. This is much more obvious when you think about a Turing machine reading all the way across multiple lines of tape, right? It's got to be storing a lot of things in its head, if you were doing a lot of mental math, in order to just make one tiny update at a time to each of the characters. I think that's all I'll say about that. So we have this current existing relation, and we're just going to use a power set. The power set's not too complicated, but what are we going to do? We're going to take every possible action. So every time I read a character and I'm in a certain state, if it's possible for me to be in multiple characters in multiple states, no problem, I simply do that. This should cause you a great amount of anxiety immediately, because it should occur to you that this Turing machine now has to maintain a power set of its own states, and it also has to maintain arbitrarily many branching tapes, because it can be writing different things to the tape. This is much, much more complicated than a non-deterministic finite automata. And this would be a huge problem for us if we hadn't just demonstrated that we can use an infinite number of tapes, or sorry, any finite number of tapes, a functionally infinite number of tapes, which is very different from having an actually infinite number, right? So, what are we going to do? The NFA and DFA are equivalent in power. And the way we showed that was we had a massive proliferation of states. But the NFA and DFA only used states to think. They didn't also use the tape. So in addition to having more states, we're also going to have more tape. The PDA and the deterministic PDA are not equivalent in power. And the reason for that is that the PDA could, it had this problem where there were cases where it would have to go back in time to see if it was halfway through a word, right? We don't have to worry about that with the Turing machine, because the real thing that was holding up the PDA is it could only read and write from the top of the stack, and it could only go forward. Turing machine has none of those problems. It can go back and forth in both directions on its tape, and it can go back and forth both directions on its stack, which is just an additional tape, right? So, for this reason, the non-deterministic Turing machine and the Turing machine are equivalent in power. Every once in a while, you'll see someone call them DTMs. I'm much more accustomed to people specifying if they're talking about deterministic or non-deterministic finite automata. I feel like everyone just uses Turing machines and doesn't worry about it too much, and you just like randomly use non-determinism in the middle of a proof if you figure out you need it. Let's write the theorem and see how we're going to structure this. Okay. So we're going to use the same notion of T recognizability. Do you want to notice we're not using T decidability for any of this stuff, right? These are all these things might never halt. We don't know. We don't care. But certainly if the multi-tape Turing machine never halts, we don't expect the single-tape Turing machine to halt. Right? It is trivial for a non-deterministic Turing machine to emulate a Turing machine, obviously, right? It simply only does one of the possible things. So we just do a cardinality cap on delta. And what cardinality is that? That is the cardinality of the set that contains the possible states. So each state goes to at most one possible state, no branches, no non-determinism. So here's the theorem. We're just going to do a conversion. Okay. The way to think about this, I think, is there's actually a form of logic called CTL, and also CTL star, which stands for computational tree logic. I used it a bit in my research. It's a sibling of linear temporal logic, which is a logic that has a notion of time in it. It's very useful having notions of time in computers because sometimes you want to see if your code's ever going to return, right? This partially addresses the halting problem. But there's this notion that when we look at any given program, there's some tree of possibilities it goes down depending on its input, right? So let's look at the example of fast exponentiation by squares. This is exponentiation by squaring, and let's see if this code actually works. We're going to give this an alias. Okay, so what I've written here is an exponentiation function, and it's very fast. It's much faster than the built-in one on large numbers. And why is that? Well, because it uses the power of branching. So what this does, and you've probably been familiar with it, is that 2 to the 5th equals 2 squared times 2 squared times 2. We can split up large exponentiation numbers into smaller exponentiation numbers. And we can say also 2 to the 8th equals 2 to the 4th times 2 to the 4th, right? So we can always split these up, which means this is the same as 2 squared times 2 squared times 2 squared times 2 squared. So we can recursively split this up into smaller operations, and these operations can be much faster, right? And one of the benefits of this is what we can actually do is, well, we only have to calculate 2 to the 4th once, and then we only have to square it. And so this is much faster than exponentiation by repeated multiplication, which is the competing methodology. What I call the inputs, A and N, okay. And the way this works is if N equals 0, return 1, because anything to the 0 is 1. I'm going to put a semicolon at the end of this line because I think I'm allowed to. If N equals 1, return A. And otherwise what we do, we're going to recurse. We're going to return A times X by molt A and minus 1. Okay. And this is going to do much of the same thing. X by molt 2 to the 5th and 5 to the 2nd. E is pretty fast, so we can take 2 to the 100, 2 to the 1,000, 2 to the 10,000, and it seems pretty crisp. I'm guessing this is going to slow down a little bit. And it crashes almost instantly, right? I don't even know if it can do 1,000, right? So this is the difference between having computational branching using exponentiation. We want our Turing machines to be able to do this, and so I'm using this as the motivating example for it can be the case where you don't necessarily know which state you're going into next. Each one of these things basically corresponds to a state. You remember when you were writing some examples earlier, your lines of code were very close to states, right? And so essentially this is what? This is a symbol we read on the tape. This is a state we transition to, and we write this symbol to the tape, and then the Turing machine does x, y squaring again, and it proceeds recursively, right? So how do I think about this? I call this the one case, the A case. This is the even case, because this is even numbers, if n% 2 equals 0, right? Are you familiar with that notation? See if it's an even number?
Yes.
Okay. And so this is the odd case. So I call these 1A, even, odd. So we're going to break these out, and we're going to say, well, why don't I just compute all of them at the same time, and I use magic to guess which one I should have done? Because that's what non-determinism is. It's magic, right? So I just put all this stuff in one line, and I'm going to magically figure out which one of them I'm supposed to use. Okay, no problem. We're going to think of this as a growing tree. Every time we compute this, we're going to recursively put something, and this is a recursive call. This is a to the 4th power times n divided by 4, right? Versus a to the 2nd power. This is a times a, so that's a squared, to n over 2, right? So this is going to keep recursing, and we're going to have a bigger and bigger computational tree here. But we're just going to keep looking at magically the correct line of thinking, right? Without ever considering any if statements, without ever taking any transitions. So I think of this as follows. Beginning from some start state, I go to a few different states, and I'm going to note these states by the names I refer to them as. There's the 1 state, when I raise something to a 0th power. There's the a state, when I raise something to the 1th power. There's the odd state, and there's the even state, which corresponds to the odd and even things. I can write if statements and check all of these, or I can just do all of them at once. Now, there's one complication with this, right, which is that both the odd and the even state are themselves recursive, which means after progressing to the odd state once, I can also progress to the 1a odd and even state again, and I can also do that if I progress to the even state. So I have sort of this branching computational tree, if this makes sense, where I just take all possible if statements. And it keeps growing, and this is just the graph structure of a tree, right? It is not, you could argue it's a directed acyclic graph, because maybe some of these trees reunify, right? But it's just like, you know, at any point in time, there's 4 possible ways I can go. I don't know which way I'm going. But if I'm executing non-deterministically, I'm allowed to cheat, and I say, oh, I just pick whatever the correct way is. And this is the correct way. We just say this is the correct way. This is one of the correct ways. So you say, oh, I'm just going to happen to go, I think this looks like odd, odd, A. Done. Right? We can think of this quite easily as saying, well, we have the 1 state, and we have the A state, and then we have the odd state. We non-deterministically realize we should be doing the even state, so that even state recurses, and it has an entire copy of the computation again. And I write this to what is an awful lot like the equivalent of a second tape, right? I put in my tape break symbol, boom. And remember, I can write arbitrarily large amounts of input to any one of these tapes. It's just slow and painful. I just have to scoot everything over one at a time. So it's like, this is a lot of work, but I can do it. So, what am I going to do additionally? I'm going to replace the tape break symbol with something else. Each one of these automata, each one of these Turing machines that I'm simulating, it has some internal state. It has the thoughts it's thinking at any given time. And I need to record that somehow because my Turing machine can only hold one thought in its head at a time. It can only hold one finite state. No problem. And you're going to love this because you've been conflating states and letters this whole time. I'm going to create a letter that corresponds to the state and then write the state directly onto the tape. Okay, fine. They are the same thing. You win. Okay. And so if I was currently in state Q sub I, right before I changed which tape I was non-deterministically proceeding on, I just simply write Q sub I, some symbol that denotes the current state I'm thinking of. I write that, and I use that as the tape break symbol, because that has to be unique from all of the other symbols, or everything blows up. And over here we have another tape that's in state QJ. And then all I do is I take turns going through all of my tapes, and I do one line of code on each of them, and I have a growing number of tapes over time, any finite number of tapes. But if I'm recursing over the natural numbers, I'm never going to have an infinite number of them, right? It's always going to be some countable number, some countably finite number of tapes. And I'll just keep updating what state I'm in, performing one computation and copying everything down. And it'll be very, very slow. And in fact, it may even crash an actual existing physical device. But if I'm clever enough, I can calculate anything I want. Well, let's put another 0 in here and see if it can handle it. No problem. Okay, we got it. There's your halting problem. Will this ever return? I don't know. I don't know if the computer can handle that number, right? I suspect probably the terminal will have a hard time before the internal mathematics will have a hard time, right? But this is only about, what? It's another digit on 2 to the 10th. No, that's going to be quite large. Okay, yeah. Because there is going to be...
I think the terminal won't.
Yeah. But, here's a good example of a halting problem. We know this will halt. We know that's a finite number. The computer has no idea. It's just going to keep going until it gets one, right? Like, let's give it a break. I felt it warming up. That's also a good way to make a heater. If you're cold in the winter, just do it. Okay. All right, so we store state as a separator. We create a new tape on branch. And what does create a new tape mean? Oh, that actually just means dropping tape break symbols and copying everything down, right? It doesn't matter if you consider yourself to have one or multiple tapes. It's identical. So here we go. A is T recognizable if some non-deterministic Turing machine recognizes A. It's slow and it's a lot of work, and we don't care because Turing machines are already not performance optimized, right? In fact, there's no real reason to believe that if we invented today a non-deterministic Turing machine, there's very many tasks at all that it could do faster than existing hardware. Of course, it'd be better at factoring numbers, and some of the things we know are hard, right? But in practice, every computational workload that's ever been delivered to a computer is so optimized for our existing hardware, they'd be faster than non-deterministic Turing machines anyways, right? So here's an aside. I cut a little bit of content here. There's something called a Turing enumerator. It has one additional thing, which is called a printer. It has an output-only tape, and that's used to generate languages. So the linguists like that one a little bit better because they don't really have a recursive enumerable formulation. So they use Turing enumerators. You can do that as an exercise, and that's a stretch break. Let's take a stretch break, and we'll assess how many minutes we have left today. It is 3:40. Oh, we're on pace, right? Yes, this thing's supposed to start at 3:30, and this is a shorter one. Okay. All right, do you need a break?
No.
Cool. I'm going to run to the bathroom real quick, and then we can get back to it. If you have any questions, be ready to ask them when I get back. Okay. I'm making some effort, because I think it's reasonable to do so, to just like tell you random assortments of facts that are loosely related to theory of computation, with the understanding that theory of computation is not often utilized in practice. And if you're going to know about theory of computation, it probably makes as much sense to know some of the historical context as the actual technical content. This lecture of, I'm envisioning us as having 22 lectures while we're here in person, right? This is sort of the most in that way. I'm going to show you sort of an assortment of quotes of how people have talked about the Turing result. And this is all motivated around the Church-Turing thesis, which is the thesis that invented computer science, essentially. That is that these Turing machines do this thing called computing, and we can make a machine that does this thing called computing. And this advancement, essentially in 1936, even though there were Turing complete things before that, it was considered relatively shocking at the time, right? Oh, you can have an abacus that can actually think, right? You know, and why not? Why can't you make a mechanical device that can add things together? But I think it was not obvious, and then it became obvious to Turing, and then Turing convinced everyone. And so I'm going to give you a bit of a context for that. I was somewhat surprised to see theory of computation being sort of the first course required for this MS. I have designed another MS, and that MS is essentially 9 software engineering frameworks stapled together, and some of them are more related than others. So this is a different kind of MS, and to me, seeing theory of computation makes a lot more sense, meeting Stacy and William, or Professor Yin and Idicus, I don't know Stacy's last name, and seeing that they are mathematicians and they had to put together an MSCS, and this is what they came up with, and this is the content they'd be familiar with. And so sort of trying to link all of those things together is like, I'm going to keep trying to give you examples of like how theory of computation applies to current modern computer devices in a way that I hope this is useful to you, and it is also preserves sort of the theoretical rigor of the program. This is completely non-technical. There's no code, there's no law tech or anything in here. There's a series of quotes. But this is probably like, there's 2 or 3 scientific theories that I always articulate to people are the most interesting, and not even just students, but like, I remember like my partner's college roommate visited us and was like, hey, what's your favorite scientific theory? I didn't say Church-Turing, but it was one of my favorites, right? There's also one called the Sapir-Whorf hypothesis, which is a linguistics hypothesis, right? And it's actually very similar to this in some ways. So the Church-Turing thesis was a big deal when it happened. It's the only reason computer science exists, and so it makes sense to launch a theoretical or academic Masters of Computer Science in that sense. I'm expecting your plans are to probably go into something like software development when you graduate. And so I don't know how much you'll use this in real life, but it's going to be an enriching experience knowing it, just in the same way that liberal arts is an enriching experience for people, right? There's more to life than just getting a job, and there's ways to appreciate your job you can only do if you understand the historical context. So that's this lecture, and there's no way to skip this. This content is a little bit too important, and it's probably the only reason to learn theory of computation, right? So we're going to be a little bit different for that reason. I'm also running out of voice, so I'm probably going to move us up to a target like 5 o'clock completion or something, and we'll see how that goes. If you still have brain left at 5 o'clock, I'll tell you something to work on this evening, and you can do that or not. Okay. There are 2 components of this. One of them is the Church-Turing thesis, and the other one is this thing called the 10th Hilbert problem. The 10th Hilbert problem is just going to be an example of something that was posed decades before the Church-Turing thesis and didn't even make sense until that thesis was arrived. One of the senses, we'll say, or like feelings people often have about computer science is that prior to the discovery of the notion of computability, there was a lot of problems that suggested we needed to have a theoretical approach to answer this problem, and the theoretical approach didn't exist. And it's not even clear there were people particularly working on actually solving that theoretical problem, because it was non-obvious, it was a gap in the literature. And I think like when Professor Sipser talks about this, like I think his perception is like, ooh, there's this kind of obvious gap around factoring. Like there's these questions we like really clearly can't answer, and they seem a lot easier than some questions we can answer, right? So computability is one of those first things that came in. The AI people are going to claim they found one of those, and I don't believe them. I think probably the next one that's going to be really interesting is, geez, I don't know. Like, there's some sort of way that we should argue that multi-core processing is considerably more interesting than all of the GPU processing, probably. And so I think the cloud computing is changing the way that people think, right? I wrote one complexity theorem ever, and I sent it to Intel Corporation. And they said, how fast can this thing run if you have an infinite number of CPUs? And I was like, oh, that's a very, very interesting way to ask how fast something is. It's not how long it would take one CPU. It's, we are the CPU company. We can run your code on as many CPUs as we want. We need to know how fast it could be end-to-end if you can be as parallel as possible. And it turns out my code that took 24 hours to run on my device, I was like, oh, this runs in almost exactly 8 minutes. And they said, oh, we can do that. We have an infinite number of CPUs, so we can run in 8 minutes. Right? So I think that's probably the next step. But what is the Church-Turing thesis? One of the problems with the Church-Turing thesis is it's not written down. It's completely unclear what it means. People just refer to it as an abstract idea. I'm going to read this verbatim to you, and think about what you think it means. The Church-Turing thesis concerns the concept. It is about an idea. It is not a thesis, it is not a theorem. Or it is a thesis, it is not a theorem. The concept of an effective, something that can do things, or systematic, something that can be described, a closed system, no inputs and outputs, that executes in isolation. If I build a device and put it in a room and leave and come back, it is finished computing when I return, right? Mechanical. Turing was the one that was most interested in mechanical, right? Gödel, Church, they didn't care if it was mechanical or not. They were just writing down mathematical logic, right? Turing said, I can build one of these things. I can go out and I can take parts and I can construct one, right? A mechanical method. And it is used in, we say logic, mathematics, and computer science. We should not omit philosophy and linguistics, which are also directly impacted here, right? Probably logic is just referring to the subset of philosophy. But the Church-Turing thesis is a philosophical result that came out of mathematics. It is interesting that there were things that were thought that only humans could do that were fairly easy to do with a tape and a head, right? It is also strange to say that the Church-Turing thesis concerns computer science when it sort of predates computer science as a concept, right? It invented computer science. Before that, there was computability, or automata. So, ineffective and its synonyms, systematic and mechanical, are terms of art in these disciplines. That is, they don't mean anything. They communicate an idea or a sense or a feeling, right? When we say mechanical, we don't mean gears. We mean Turing could imagine one actually existing. But we only mean Turing. We don't mean we could imagine one existing. It only matters that Turing could imagine this, or someone other than Turing. Post could as well. And so a method or procedure, and here's our only sort of script M, right? The machine M, the Turing machine M. A method or procedure M for achieving some desired result, right? M is set out in terms of a finite number of exact instructions. Exact instructions is tough, right? So I work with students a lot, and I frequently am confident that I am being completely unambiguous, and the students are frequently confident that I am not communicating clearly, right? And so an example of a statement I often have with students is I will say, on line 23, what is the 17th character? Because I see that's where the typo is. And oftentimes students cannot find that character, and that is surprising to me because of how I think, right? But we should have a clear notion of what exactness means, right? And I think one of the ways to determine exactness is perhaps, from the linguists, we would say, if I have instructions and I can write them down in an email, and you can't see my tone of voice, and you don't know what dialect of English I speak, and you don't know what type of keyboard layout I have, perhaps you can get that email and you can build a clock from a kit given just the instructions in that email. Perhaps that's some notion of exactness, right? One of the things I often see in the field of computer science is computer engineers being sent from a company in one place to a company in another place to help build a factory that creates something like a hard disk drive. When I was at Seagate, right, there were people that trained in Longmont, developed the process to build a hard drive, and then went to, I believe, Thailand, where the hard drives were made, right? And the reason they did this was no one could figure out how to write down in an email how you actually built the hard drives. They had to send humans. You can't do that to a Turing machine. If you have to send a human to teach another human, that's not something we can train a Turing machine to do, right? Now, I suspect in those cases we could have trained a Turing machine. It was in fact easier to just use humans, right? But nevertheless, right? So a finite number of exact instructions. That also means not infinite. Really what this means is it can be stored on a hard drive, any hard drive, or in fact any number of hard drives, but not an infinite number of hard drives, right? There's a sort of comical result that one of the fastest ways to move information across the country is to ship hard drives, because that's still faster than Ethernet, right? You just have to move enough hard drives at a time. And then a truck driving is moving faster than the effective speed of light, right? Okay, and then we say M will, if carried out without error. So we are allowed to assume we don't make mistakes. So this is not a notion of fault tolerance or anything like that. And this is important because these later results about impossibility, many of them concern fault tolerance. They're like, well, show me the computer that keeps running if there's a power outage, or show me the power grid that never goes offline. And you say, I have neither of those two things, right? So Turing was unconcerned with the power going out. Turing only cared if the machine is running correctly, does it work? And so M will, if carried out without error, without making mistakes, without raising a value error, as we did in Python, produce the desired result in a finite number of steps. But we don't know how many finite number of steps. So maybe it is one less than infinity, right? Which happens to still be infinity, but like some infinity scraper, Googleplex number of steps. I think I could pull up some other slides where I wrote out a Python statement that was not even a line long, and I said, this will run longer than the heat death of the universe. It's just not that hard to do that. Let me show you one simple example. Here is a simple sequence that increases. We begin with 1. The next one is 2 to its own power, that many times. Then we do 3 to its own power, its own many times. This mathematical operation I've referred to as supernation, as in it is more than exponentiation. It might also be called hypernation or something like that. All right, here's another one. And I think this runs forever. It's a very large number, right? So 4 to the 4th is 64. So that's 64 to the 64th power. It's pretty big, right? We can actually work it out, right? Because this is... Ooh, no, I don't want to get off by a little bit, right? That's 64, no, because it's 64 to the 4th to the 4th, so it's much more than that, right? Yeah, what's 4 to the 64th? That's 2 to the 128th. And so that's 2 to the 2 to the 128th. This is right around a Google. This is, right? 2 to the 2 to the 128th. No, it's much larger than that. This is around a Google. This is around a Googleplex. And so this will run 10 to the like 40th years or something, right? So I think like there's not enough energy in the universe to run that computation or something, right? Okay.
It's Google, yeah.
Yeah. And I think like you might be able to do something where you do like can you approximate it? Yeah. Yeah, so, right, that's considerably more than a Google, actually. Right.
You have to add one more.
Yeah, and we need to do one more, right? And so this thing's never going to happen, right? Yeah. Because it's not even this squared, right? It's that to the fourth, right? It's too big. Okay. Okay. We additionally claim, and this starts getting pretty weird, and this is also where you start seeing like the way people thought of things maybe in the 30s. We sort of didn't have access to some of the theoretical techniques we have now, right? But we can say M can, in practice or in principle, be carried out by a human, being unaided by any machinery except a paper and pencil. And like, what does that mean? Like, how does the paper and pencil help, right? Like, we know humans can remember large numbers, right? Like, this is an odd restriction. And like, what do you mean they can't use an abacus, right? Does the abacus increase the computational power of a human? What about a slide rule, right? There's these old mechanical calculators. Like, do those really matter or not? But like, pencil and paper is fine. But it's fun to see how they were thinking of it, right? Because to me, it looks like Turing was looking at a specific problem, and he was trying to crack codes in World War II. And he's like, well, I can sort of hire 1,000 undergraduates, but the 1,000 undergraduates don't have a PhD level of training, right? So if I need someone with a doctoral in mathematics level of training, I actually only have 15 of those, right? So any sort of thing that I solve for a Turing machine, some human needs to be able to do it, or I need to be able to make a machine that can do the things the human can do and use the humans to do something else, right? So it's almost as if it's solving this like economics problem, where it's like, oh, I don't have enough humans that can do the thing. Can I use some sort of force multiplier, right? But they wanted to specify it in some way that a human can do it, right? We require no insight, no intuition, no ingenuity, no creativity. This is getting very close, and this one became much more interesting. These are all the things that the large language models do not have. So essentially, if a large language model can do it, I argue a Turing machine can do it. And if you're going to argue to me that the large language model has ingenuity, I need to see a proof of that, right? I need you to demonstrate that it can tell me what the largest prime number is or something like that, right? Okay, so let's give some credit here. This is from the Stanford Dictionary on the Church-Turing thesis. I can find no credible sources that there's a specific specification of the Church-Turing thesis by Church or Turing, or that anyone referred to it as the Church-Turing thesis in their lifetime. Here's another one. This is a direct quote by Turing in 1938, 2 years after the machine, right? We shall use the expression computable function. So he's thinking of functions. And with the deterministic finite automata, I really stressed the notion of function. This takes bit strings to bits, bit strings to bits. Turing is thinking of it that way as well, and you can see it in his notion. I've seen many people talk about Turing or claim to understand Turing or Turing's work in a way that I found unconvincing, because I know Turing worked for Church, and Church did everything he did with only functions, only with the lambda functions in his lambda calculus. So I'm quite confident Turing was thinking of everything in terms of functions. There's been some later efforts to claim that the Turing machine is like the origins of object-oriented programming, and I find that quite questionable, because there's no objects or interfaces in there, right? It's taking bit strings to bits. And so I think Turing was thinking in terms of functions, a mapping from one value to another value. That's all. Nothing in between, didn't care about the intermediate. And so we use the term expression computable function to mean a function that is calculable. They don't say computable yet, because that word doesn't mean anything. Calculable, that can be turned into a result by a machine. And we say effectively calculable to refer to the intuitive idea without particular identification with any one of these definitions. What does that mean? We don't care if it runs on a Turing machine. We care if it runs on anything. And then Turing will later claim if it runs on anything, he could run it on a Turing machine. And he did convince everyone of this. And he convinced everyone of this by essentially showing equivalences to the existing models of computation. Here's an interesting definition of algorithm. People talk about algorithms a lot. I use algorithms for all kinds of things, right? So I talk to my undergraduate students when they're signing up for classes. So you don't get to choose classes in this program, and I don't know if you got to choose classes to a great degree in undergraduate. Students in engineering schools frequently don't get to choose their classes. At a liberal arts college like Lagrange, they probably get to choose every class, you know. And I sort of teach a more engineering class in a liberal arts college, and so I often tell to my students, you should follow an algorithm for selecting your classes. And to me, the algorithm is quite simple. You take things that are required to graduate before you take things that you don't, right? And this is a Turing complete algorithm. I can write this down in an email, and a student can follow it without asking me for clarification, right? So that is a computational procedure. It is not a computational procedure I program into a computer. No, I program that into a human, right? And the human can execute it, right? And a huge part of getting humans to execute algorithms is actually persuading them it's in their best interest. The graduate on time is a very compelling interest for most people, right? But there are other algorithms as well, right? I think a lot of etiquette is algorithms. Like, oh, the expectation, you say, hello, this is my name when you answer the phone, right? That is an algorithm, right? Something humans can do. So we say no computational procedure will be considered an algorithm unless it can be represented as a Turing machine. Let me give you the example of something answering a phone. When I invoke Python, the first thing it does is it does not put up the command prompt. It says, hello, my name is Python. It introduces itself. It gives me some simple directions. That is as much the notion of an algorithm to me as a for loop is, right? We want our computers to interact with us the way we expect to be interacted with, and we can program them to do so. This is the Google DNS server, right? It didn't have to say this, right? It doesn't have to say, hello, here are the contents of your package, goodbye, right? This is a computer following social norms written by humans. No computational procedure will be considered an algorithm unless it can be represented as a Turing machine. But I can represent all of these things as Turing machines, because I can produce a state that says, here's a sequence of states. I need you to output these values, right? If this is what's written on the tape, I need you to write pinging before it, and I need you to write with 32 bits of data after it before you do any other computation. I can express that as an algorithm. And it's not even particularly difficult to do that, right? We say IP equals, and then we say print pinging IP with 32 blah, 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 right? We can express that as an algorithm. It's the same idea. Allegedly, Church said this. I couldn't find the source of it, but people believe Church said it. And I think this is probably the reason Church and Turing's names are both on the thesis, right? It seems like Church said, if it's an algorithm, a Turing machine can run it. And Turing said, if it's an algorithm, a Turing machine can run it by definition. So we believe them, we accept this. Here's another quote. This is also by Turing. Very interesting extension of his earlier text, right? So this is a footnote to the earlier one. It was stated that a function is effectively calculable if its values can be found by some purely mechanical process. He strongly preferred the term mechanical, and you see his strong preference for mechanical over the computing norms. He says, we may take this literally. And he means, I will build a machine that can follow these instructions. To me, this neatly dodges the very interesting linguistic effects, which is, what do you mean give instructions to a machine, right? And I don't know what Turing meant, right? Later on, you see he's using like the bomb decryptor, BOMBE. It had like gears, and you would set the gears in certain configurations and then press go. And so he's providing instructions by putting gears in certain arrangements. To me, you don't really give humans instructions that way, so that was a little bit novel, right? But it was very important to him that it was completely mechanical. I don't think of things in those mechanical sense, so I do think of them in this linguistic sense that the lambda calculus had. Oh no, my leg's falling asleep again. Okay. We're shifting in our chair. Okay, there we go. You cozy? All right. Okay, so you have a purely mechanical process. And so what he does, and this is the invention of computer science, right? If it can be computed, it can be calculated. I don't know, to me that's a recursive definition. I think this probably seemed more exciting to people at a time. But he's essentially claiming that any numerical operation can be performed by a machine, right? I think this was a big deal. My sense is that there were a lot of mathematicians in the 30s going around asking each other to manually calculate the square roots of large numbers, and they thought this was what math was. In a way, I think, I like to believe what happened, is Turing showed that all of the boring parts of mathematics can be done by computers, and now the mathematicians get to go do cool things like field theory and invent cryptography. The computer scientists get to go do things like write down what they actually mean. And no one is sitting around taking square roots of numbers for fun, which is just like not an interesting thing to do with the human brain, right? It's much more interesting to do the higher level of thinking, where we do abstract mathematics, or we do abstract computer science, or we actually build software, or we actually create numerical fields, right? So my hope is that this line led to that. I don't know if that's true, and I'd actually be curious if like Professor William or Professor Stacy were around, like what they think about this. Like, in 1938, did mathematics change from adding really large numbers together in your head to writing proofs? Because if you did, that's a very big deal. Every effectively calculable function is a computable function. This was much later. People weren't saying stuff with this level of clarity until the 80s, and I just want you to look at this. That's Turing describing his own idea, and we give him credit for the Church-Turing thesis and name, right? This is how people were describing it by the 80s when they think about it. If it can be calculated, it can be calculated by a computer. There is no calculation a human can do that a computer cannot do. Sure, I guess I believe that. I don't know. The lambda calculus. I have to show you the lambda calculus. I think of the lambda calculus quite simply, and it is in two ways. This is a capital Greek lambda. We say it is equal by definition to what is this? This is, we take lambda and we substitute lambda in some expression. Lambda is an element of the variables. Those variables are the same as the context-free grammar variables. Those are the same as the elements of gamma. So we still have the notion of a letter here. And what is m? M is an expression within the lambda calculus, and you'll note this is the first one of these we've seen. This is a recursively defined set. Church used recursion, Turing didn't. I have such an easier time with this because I like to think about things recursively, right? Okay. So what does that mean? We are substituting some value for x in some expression. The values of x are variables. Church, to my knowledge, used two terms for this, and I think he called them definition and application. It is very simple to see the difference of these now with modern languages. This is the simplest lambda expression, the identity function. I can't call this x. I call it f. This is definition. This is application. One of the things that Church pointed out is you can actually build the natural numbers out of these things, because you can just say, you don't need anything in there. You can do it on nothing. And I think this might break on nothing, so I'm going to provide Python none. You can just say that's 2. And so you can say, I have 2, which is f of none. And so Church was able to construct the natural numbers with computable functions, and that was pretty interesting, right? And you'll see this is very similar to the set theoretic formulation, where we say this is 0, we say that's 1. Oh, I'm not allowed to do it in Python. You can't put sets inside of sets in Python, but you can in math, right? Well, I can do this. Oops. We say that's 2, and we say that's 3, and so on, right? So one of the things that the mathematicians and linguists were doing at this time is they were building numbers out of languages, right? I see that quite strongly here, where it's like, yes, you are very, very specifically, to me, trying to build the natural numbers. Both of these things are recursive. That is recursive, and this is recursive. I suspect Church was actually going for the real numbers, and that's why he has 2 recursion things, and just didn't get them. And then we note over here, what is this? In addition to a lambda expression being permitted to be a function, either the definition or the application of a function, it can also just be some value. No separate alphabet here, only variables. If Church needed to use a number, he had to build the numbers out of functions. He didn't use numbers as an elementary basis, right? So Turing's using binary, Church is using functions. They're both getting to numbers. And then Church and Gödel both see the Turing machine and they're like, oh, I could have been using numbers the whole time. That's a lot easier than what I was doing. Lambda of x dot x represents the identity function. I wrote that right here. Lambda of x. This is the Python version of dot, because dot is already used in Python for something. I was imagining, is that actually true? Oh, I guess they're worried about doing this.
Call out from the function.
Oh yeah, I can say like.
When you're doing like append, dot append.
Yeah, so I have f.
F dot append something if you have to push into this.
Yeah, I can do that. All right.
State.
Yeah. Okay. All right. Lambda of x dot x represents the identity function. Term of x.
Lambda x dot m or lambda x dot x.
So this is an example of a function. This is the abstract notion of a function.
Oh,
Yeah. So this is any possible lambda expression. I don't know why we use m there, and I think the reason we use m there is that lambda expressions are logically equivalent to Turing machines. So any function is as powerful as a machine. Because of course there's the Turing machine that returns itself. It's the one that accepts remedially, right? Because there's already something on the input tape. Okay. So we call this an abstraction or a definition. Yeah, I'm sorry, I should have been more clear. I was saying definition and application. They didn't use that term. They used the term abstraction and application. The notion of using definitions came much later. There's a later result called the Curry-Howard correspondence that demonstrated programs and proofs are equivalent. And that was when the term definition came into computer science, because definitions is the formal mathematical term. And they said, oh, that's actually what we're doing with definitions. This definition, wherever it is logically equivalent to the proof for all x, x equals x, right? Which is not a very interesting proof, but there are more interesting proofs, right? So then we can take m to n, which is an application. We take one lambda expression and apply it to another lambda expression. And that is what this is. And we do variable substitution, and then we resolve all of the namespaces and so on. The reason it took Church so long to get these proofs to go through is he had to use extremely complicated variable renaming to avoid namespace collisions. And this extreme complication persisted right up until the formulation of Lisp, which is quite close to the lambda calculus, in my view, maybe not in others. So he essentially couldn't get this to work. And he did eventually get it to work, but he didn't get it to work until him and Turing worked together and already had a Turing machine, right? So it's kind of strange to say it pre and post states, right? But to me, versus a Turing machine, why would I so much rather write this? I don't care how complicated the variable renumbering is, because it's so blasted annoying to write these delta operations, right? And they were writing the delta operations before they had access to JSON notation, which is how we write them now. And I think like it should be quite clear that the reason the universe converged on JSON notation, which is the way objects are stored in the two most popular programming languages in the world, both Python and JavaScript, right? To me, that's one of these similar naturalistic results where when you have convergent evolution, when you had the lambda calculus and the Turing machine converge, we should be equally convinced of the correctness of JSON when we see Python and JavaScript converge and both use JSON, right? So absent JSON, it's very odd to me to not use the lambda calculus. So the 10th Hilbert problem, let's talk about this. Okay, gotta take a drink, gotta do a time check. Okay. Okay. The first problem is pretty interesting, and it remains partially unresolved, right? And so, okay, I think like in like 1903 or 1900 or something, there was like a math conference, and I think they had like one conference a year then. It's not like now where there's like a conference every couple weeks and they're hyper-specialized, right? I think there were like 200 mathematicians in the world and they like met once a year, right? And perhaps that's why it took 36 years to come up with the Turing machine, right? Because I think if I locked one grad student in a room and said you have to solve computability theory, they'd be done in like 18 months, right? But I think there were very few grad students in the world, and they were all working on different things, right? So Hilbert is some mathematician, and Hilbert's homework assignment before the next math conference was come up with 20 hard problems, because that's what they did. And so the first one he came up with, just to give you some context on this, is there some set that has cardinality between the natural numbers and the real numbers? And the answer is we don't know. There's this thing called the continuum hypothesis, and it actually depends on how you define the natural numbers and the real numbers. It took a long time to get that proof. Hilbert proposed this around 1900, and Cantor, who was an earlier mathematician, had just demonstrated that the natural numbers and the reals were different sizes, right? Because it was thought they're both infinity, so maybe they're the same size, right? There's this thing called the continuum hypothesis. I don't really care about the continuum hypothesis. Some people do a lot. Don't tell William and Stacy I don't care about the continuum hypothesis. It might matter to them a lot, because not every mathematician, but the ones that care about it a lot, right? The next one was, are the axioms of mathematics consistent? And it's like, come on, Hilbert, what's that even mean? Well, anyways, Kurt Gödel actually went in on this and demonstrated not whether there was consistency or not, but that it was impossible to demonstrate consistency. And he demonstrated that with his famous incompleteness theorems, which are an independently interesting result that I think is out of scope for this class. I would probably say that's a philosophical result. I wouldn't even say that's a mathematical result, because it's a result about mathematics, but it's not a mathematical result, right? My impression when I'm teaching a lot of these things is there's a strong underappreciation. The linguistics gets in a little bit, I think basically due to the cult of personality around Chomsky and how he was so obviously so much smarter than everyone else for so many decades, right? There doesn't seem to be a corresponding philosopher that's held in that same regard, but there's a lot of things that like look an awful lot like philosophy to me, and I think like as computer scientists, we at some point should say, yes, it is up to the philosophers to determine if computability theory is interesting. We just study the computability theory. We don't care if it's interesting or not, if we find some application of it. 3 was something uninteresting. 4 is determine the solvability of a Diophantine equation, and the Diophantine equations are polynomials with integer roots. So does 4x to the 4th minus 4x squared equals 0 have a root? I think it does. It's like 2 or something, right? These are Diophantine equations. They can be expressed for arbitrary polynomials. And arbitrary polynomials are of the form, this summation, so we add them together. It's a numerical summation. It's over all n, so up to arbitrarily high number. We have some indexed value, so this is an integer multiple, and then we raise x to the k. And so that's how we express polynomials. And we ask, does it have a solution that is equal to 0? And we restrict it to be the case that all of the k values are integers. And yeah, that's interesting. Okay, so let's look at 1900. The problems were proposed in 1900, and they were proposed to be solved in the next century. This problem was proposed and not defined. Wait, I skipped something. Okay. The Diophantine problem is interesting, and I didn't specify this here, because the question was, can we compute the answer to this problem, right? And it was proposed in 1930, and Hilbert didn't say what compute meant, or calculate meant, right? So there wasn't even a meaningful way to answer the question of like, hey, can we actually calculate out the answer to this problem, until the Church-Turing thesis comes out in 1936 to 37. That was the first time, not that the answer to that problem was known, but that even that problem was defined. It didn't even make sense to ask, hey, can we figure this out? What does it mean to figure that out, right? I think in 1900 you sit down and you would have to try all of them. Remember, they didn't have for loops yet. They didn't have multi-tape Turing machines. They had no way of calculating over every possible number in a series, right? So, Church and Turing come in 1937. They say, hey, we have this notion of computability, and it can be applied to the Diophantine equations. Matyasevich, who I don't know anything about other than that name, 70 years after the problem was posed, wrote a proof that a Turing machine cannot decide if if a Diophantine equation has integral roots, and therefore finally closed that problem. This was the 10th Hilbert problem, and it was very exciting when it was solved. It was very exciting with Gödel proved incompleteness. It was very exciting when the continuum hypothesis was first specified, and so this was an open problem in mathematics that took 70 years to solve, and the entire field of computer science, right? It is recognizable, but not decidable, which means if you don't care if you halt, you can answer this question, which is not great. That's the same thing as not knowing, right? So undecidability isn't great. We're going to use a notational convenience. Wait, do I care about this? I'm showing you something which is interesting, which is bit encoding. Okay. I'm leaving something up to you. There are 10 slides left. These 10 slides consist of me programming the Diophantine equation into a Turing machine. I'm going to do it using binary, and I'm going to go through it really quick. This is the way I encode strings. We're going to show a way of encoding Turing machines. Here's what you should do if you write a proof. I recommend just writing them in Python. If you can write it in Python, it's Turing complete, right? Or is Python your best language for you? Because you were a Python developer, right? Yeah, okay. If you want to use JavaScript, if you want to use C, if you want to use Haskell. Yeah. If you want to use this class to learn JavaScript, do whatever you want, right? 3 possible outcomes, Turing decidability, strings. Okay, stretch break. Let's start the final one for today, which is acceptance. Okay, we're shifting gears in the following way. We have now introduced the 2 automata and the Turing machine, which is not quite an automata or something else. What we're now going to do is we're going to show not how powerful these things are, but what conclusions we can come to about different models. And one of these models is acceptance. There's also emptiness, which we're going to begin with tomorrow. And then we're going to build up to the sort of most important result, which is the end of the second third of the class, which is the undecidability result for Turing machines, that there exist things that Turing machines can't answer. And so we're going to begin by doing incremental and debatably less interesting results over weaker models. And we're going to show things that the weaker models can and can't be held to have certain properties, right? Okay, so one of these is acceptance. So what are we going to do? We're going to do the acceptance problems over DFAs and NFAs. And then we're going to go home, and you're going to think a lot about push-down automata, Turing machines, and acceptance. And you're going to come back tomorrow, and we're going to do emptiness and undecidability. You don't have to know what those things are yet. They're like acceptance. Okay. The acceptance problem for DFAs. So what is the acceptance problem? Well, we're going to imagine there is a DFA language. And that DFA language, acceptability of DFA, is not a language that is accepted by a DFA. It is a language about DFAs. So we're going to take B. B is a deterministic finite automata, and W is a bit string. And we're going to write down B, we're going to transcribe it somehow, and we're going to transcribe it in the manner of the exact instructions we give Turing machines, right? So we're going to write it down in symbols on an input tape. So I'm writing down on a tape, and then I'm going to do something very close to a tape break symbol, and then I'm going to specify the bit string that is the input to the DFA. So I'm going to write down the DFA, and I'm going to pretty much write it down as big Q, big sigma, little delta, Q naught, big F. I'm going to write down the specification of the machine. Then I'm going to write down the bit string. And those strings that are of the form a DFA, I'll do it with this hand, a DFA, and a word that is potentially accepted by the DFA, that is a language that is Turing decidable. A Turing machine can read the definition of a DFA and determine if it accepts the word. We're going to prove it. And it's decidable, not recognizable. It halts. We know we're done. Okay. At least that's the theory. I'm going to wave my hands now, and I'm going to say, you can write down the DFA however you want. We know we can write down programs. You can convince yourself you can write down programs if you need to, but we can write down programs. One natural way to think of this is that the Turing machine has the same number of states as the deterministic finite automata with the most states. You'll say, there's no cap on that. It's like, that's fine. There's no cap on anything, right? It's some finite number. So really we just want to, this is a Turing machine that either accepts or rejects a string. And it accepts or rejects a string based on whether one part of the string accepts or rejects the other part of the string, which is sort of a novel way to think about this thing. This is asking a computer what a computer thinks about something, but it's a different computer. This is virtualization. I think this notion of writing proofs, it is difficult to underestimate the importance of virtualization for facilitating every single computing advancement of the last 16 years, since around 2008 when cloud computing became a big deal. All computers now run multiply virtualized on some enormously large virtualization stack. I'm running Microsoft Windows on this computer, and it's running on top of something called Hyper-V, which is this thing that's in between an operating system and not an operating system. Your computer is probably too. I don't know how new it is, right? But simply put, all these things are doing is they're looking at something in memory and they're writing to something else in memory. It doesn't matter if they're pretending to be another computer or not. That doesn't affect us. We just see the outputs. So let's think about this. So we're going to create a Turing machine, and I'm going to make apologies for this. As a rule, I try to avoid doing this, but that is multiple subscripting. That is D subscript A subscript DFA. It is the machine that accepts the language of the acceptance DFAs, okay? So this is the decider. We call this the decider. And that's why it's D, because this thing decides. It does not recognize, it decides, okay? And what is the difference between deciding and recognizing? Pretty much. Deciders always have output, recognizers don't, right? A recognizer doesn't halt, a decider does. Okay. This is how we're going to specify our Turing machines. We're going to say on some input W. We're going to check first that S is of form a DFA followed by a bit string. That's easy. We have some agreed upon way we're going to specify our DFAs. We just type check it, and then we CW. This is very similar to saying, hey, I got some function. This X is required to be an integer. So we can write these type checkers. Oops, I did mean true.
True, T will be.
Yeah, I need to capitalize it. You see where I'm going with this, right? So we're going to check that S is of some form. And we're not going to check that it's an integer, we're going to check that it's a DFA. And we have some way of doing that. And maybe it requires a large number of states in our Turing machine. We can use as many states as we want if we use a finite number, okay? This should remind us of type checking. We're going to simulate B over W using the DFA in internal states. How do we do that? Well, no problem. So we have a string, and before that we have a DFA. Let's just go to the end of that string, put a tape change symbol, and then we're going to write the current state of the DFA. We're going to write the current head position of the DFA, and that's all you have to write, because DFAs only look at those two things. So the Turing machine will look back over, it will look at a letter on the tape, and in fact it doesn't even have to do that. You can just write the current state of the DFA directly on top of the letter you're modeling, because as soon as you read it you never have to go back again because it's just a DFA, right? So this is actually quite easy to emulate, right? We just destructively update the string, and if the last character of the string is the acceptance character, then we accept, right? So we're going to simulate B over W using ADFA's tape and states. And there's any number of ways you can do this. And remember, you have access to 100 million tapes if you want them. You have access to non-determinism if you need that. Very simple. And this, of course, means because we have access to non-determinism, we can do this for NFAs, right? Okay. If B accepts, then DFA accepts, and otherwise it rejects. Why is this a decider? Well, all of the DFAs are deciders. So since we know the DFA is going to decide, this is just going to simulate the DFA and then return the same result. So we know it's going to return to us, right? Here's the example. Here's how I think of it. We have our tape break symbol. We have some bit string. We have Q, the finite set of states. We have the alphabet. You could specify that as 1 or 2 tape symbols. I don't know. Maybe you just have a tape symbol that says this thing's in binary. This isn't unheard of, right? We have a symbol in Python that means the following string will be in binary. It's 0B. It's 2 characters. No problem. We have one that means the following string will be in hexadecimal as well. Can you do this? No. Do you know if there's octal? Yeah, okay. So we have ways of specifying what sort of language we're working with. And you could argue equivalently, quotes are also, in a way, specifying a number system, right? It's just the ASCII number system, which isn't really numbers. So we specify the alphabet, we specify the delta. Delta is definitely going to take more than one piece on your tape, right? But Q naught's not going to, because this thing's just going to be an array of states, and this is just going to be one of them. And F is just going to be a repeat of some number of these states, right? So there's going to be essentially a lot of state symbols, right? And then what I'm thinking is, you read this, well, probably you copy this here, and then you read this, and you copy something from here, and you keep going, and then whatever is in here, you check to see if it's in this list here. And that's all. And perhaps you have take breaks separating these so you know that the initial state isn't an accepting state, right? Easy enough to imagine. Let's simplify this. You don't have to put this all on one tape, right? Something I like doing when I write these proofs is I don't say, oh, I have a special new alphabet that tells me where the head is. I say, I have one tape, and I write in binary on it the index of the head on the other tape. And so then I read that number, and I have one head tracking that tape, and I move over one in terms of binary arithmetic. And then I just update it when I leave, right? So those are all easy things to do. I would certainly, the very first thing I would do is copy either B or W to a work tape. Most likely B, because I'm not planning on updating B, and then I leave W on the output tape, right? So let's use some notational conveniences here. We are going to pattern match our input. You remember I initially said on input W. And then the first thing I said is type check that to see that that W is the string encoding of B followed by the string encoding of W. I don't have to say that. I can just say, if the input's not this, I don't care what you do. I'm not defining my Turing machine in that case, right? If this thing's not an integer, I don't care what happens. You know, that's your problem that you gave me something other than an integer, right? You shouldn't expect to get true, false, halt, anything else, right? We simulate B over DFA using DFA's tape and states. If B accepts, then accept, else reject. We pattern match on the initializer. It is appropriate to do this in programming languages, so it's appropriate to do this here. Let me give you another example of a Python pattern match. So it's reasonable to say max only works over things of this form. And if I give it something of a different form, it instantly explodes. That's totally fine. I never claimed I could find the max of anything other than a pair of numbers, right? And in fact, the way I should specify this is and that's legal as well, right? Okay, always appropriate to use a programming language. Here's an example. D sub A sub DFA accepts B, which is a DFA, More properly, it is the string encoding of a DFA. We don't care about that. And we accept W, which is some string, and we return a Boolean. And the only thing we do, because a DFA is a function that goes from bit strings to bits, we just apply that to W, and then we return that value. That's all. I took A or R to mean accept or reject. Of course, you can just return it directly. The only reason to show this is to denote that we're doing application. What about loops? So something we should be worried about is, can't there be an infinite loop in a DFA? Might we never halt? No, you can't. DFAs have a progress mechanism. At every single computational step, they progress one step down the list, or down the string, or down the array, or whatever you want to think of. But they're always reading more of the input, and the input is a finite length, which means these things are always going to end at some point, which means your Turing machine is going to halt, because at some point it's going to run off the end of the list and have to accept or reject. Finite string, progress every single clock cycle, it must terminate. It doesn't matter how slow your Turing machine is. It can do 1,000,000 calculations every single step. Eventually, it's going to run out of string to calculate and return. And that's good enough for us. Right? Okay. We term this theorem 10, and this is our proof. The acceptance condition for deterministic finite automata is Turing decidable. Done. Time check. The reason I'm checking my phone instead of my computer is my computer doesn't know what time zone I'm in, and I'm not willing to change it. All right, I know what you were thinking. You were thinking, wait, is the acceptance condition for non-deterministic finite automata also Turing decidable? Is that what you were thinking?
Yes.
I knew it. We're so locked in. Okay. There's one tiny problem. We don't actually have the progress mechanism that we used in DFAs here. Because an NFA can have an infinite loop that is all don't read anything. And it's actually pretty easy to write one of these out, right? You just say, I have two states, and they both have an empty string in between them. You can go back and forth forever. Not great. How are we going to deal with that? That seems like a pretty big problem for us. Because that means we don't know this thing's ever going to halt. So we somehow have to outsmart this NFA. But this NFA is not nearly as smart as our Turing machine, right? And so our Turing machine is going to be able to outsmart this NFA and make sure it doesn't get stuck in an infinite loop. And how's it going to do that? Well, you just convert the NFA to a DFA and then check that. Remember, we have a way to turn NFAs into DFAs. So we don't care. We never look at the NFA at all. We just use theorem true. Boom. Done.
We will convert.
Yeah. I just say, what do I do? And to me, this Python's quite readable. So I have theorem 2, which is called NFA to DFA. And I have theorem 10, which is the decider over the acceptance of the DFA. I accept an NFA and a string. I create something called B prime that is of type DFA. I apply NFA to DFA to the input, so B prime is now a DFA. Here's my acceptance condition. And then I simply apply B prime to W. Easy. And this is where we want to be like a little bit clever about using some of our earlier results. We could have really tricked ourselves here, right? You could have even thought, oh, I'll run the non-deterministic Turing machine over it. Well, there's no guarantee the non-deterministic Turing machine is ever going to halt either, right? But the DFAs are going to halt, and we can turn every NFA into a DFA. So it doesn't matter if NFAs halt or not. We don't have to prove that over them. We can just prove we turn them into DFAs. So always use work you've done already. Right? Okay, let's do another one. We call this E sub DFA. And what is that? Well, B is a deterministic finite automata. And separately, what else do we have? The language of B is empty. It is the empty language. It is not that it contains the empty string. That would be a different proof, right? And this is why it is important to have the difference between the empty string and the empty language. When do you want to do this? Every once in a while, someone asks me to write a program that is going to return false in all conditions, and that suggests to me they didn't think all the way through about what they were asking me for. A good example of this is like, only power users can raise their privilege level, but power users have the maximum privilege level. So I was like, that's nothing, right? If you're already the maximally privileged user on an operating system or some research group or something, why would you be able to raise your privilege level? You have the highest privilege level, right? That's like, you can set the maximum to the maximum. It's like, I know, that's a tautology, right? So these emptinesses float around, and usually they float around when someone who's like partially technical or something wants to ask for a technical thing. So that's mostly been my experience with this. I think that's a big example. It's almost always when you're giving people permissions that they already provably have, right? Okay, we term this the emptiness problem for DFAs. These are the DFAs that produce nothing. DFAs don't produce, they accept. This is the DFA that accepts nothing. All DFAs that accept nothing. We're going to make a decider, and we're going to see if it exists. So essentially what this decider has to do is, what you don't want to start doing, and don't fall for this trap, is I will test every string and see if it accepts it. Because that never halts, because you never run out of strings. And you never run out of strings of finite length either, right? Because we haven't even figured out what our alphabet is yet, right? So even if every single individual DFA has a finite alphabet, there's still perhaps potentially an infinite number of possible alphabets, right? So we can always draw some new symbol. Or we can say, oh, those two symbols look the same, but they mean something different. We were talking last night when I first got here about, I teach at a university called Willamette, and there's a Willamette Valley in Massachusetts, and it's the same spelling. So even two words having the same spelling doesn't mean they're the same word, right? So you can get in big trouble really quick when you start trying every string, because those are two different strings with the exact same spelling. I'm going to let you off scot-free on this one, right? We've been using these delta functions all day, and those delta functions are just implementing a graph. And there's this little thing we can do with graphs called depth-first search. And that's what Professor Sipser uses. I wasn't thinking about graphs because I like Alonzo Church's lambda calculus. I was thinking about functions, and I realized, well, delta is a function. I never said that thing was a graph. You said it was a graph. That's not true. I said it was a graph. I'm not going to blame you for that one. Delta is a function, and it's a function that goes from states to states. I can just take the transitive closure over that. And I think, did we talk about transitive closures? I talked about transitive closures in one of my classes recently. Do you know what a transitive closure is?
Yeah, I think so.
Oh, yeah, we did. That's the Michelle Obama case. If I'm friends with Barack Obama, Barack Obama's with...
Yeah,
yes. Why that's the case I came up with? Why was I thinking about Michelle Obama? We're just always thinking about Michelle Obama, right? Okay, so transitive closure, right? And so I was like, well, if there's a path from Q0 to Q7, I love sevens, and there's a path from Q7 to Q13, that means it's a path from Q0 to Q13. So if Q13 is the acceptance state, that means it's possible to accept, and that means there's something in the set. So all we have to do is take either the transitive closure over delta and see if there's any way to go from Q0 to anything in F. Or we do breadth-first search over the graph and see if there's any path through. The graph is a little bit easier to check. So let's do an understanding check. Can I just run B over all strings? No. Can I just run B over all strings up to some length? Yes, you can, actually. Because of the pumping lemma, you can pick some length and check every string up to that length. The problem for writing a proof is you're going to have to say what that length is. Or you're even just going to have to say that there is some such length. And that's not actually easier than doing breadth-first search, right? So I remember when I was taking my undergrad class, a lot of people were like, oh, I'll just check all of the strings. And you're like, you can't do that. And you're like, I'm going to check all strings under length 1 billion. And then, of course, the professor just like instantly produces something that has to exactly be of length 1,000,000,001, right? It's like, I create the deterministic finite automata that only accepts strings of length 1,000,000,001. And you're like, oh, dang it. You're like, fine, I'm going to go up to 2 billion. And the professor says, no problem. This is the deterministic finite automata that only accepts strings of length 2 billion.5. And you're like, you can't have decimal length strings. And it's like, of course I can. I'm the professor, you know. So never fall into that trap. If you are going to say, hey, I run overall strings up to some length, that's fine, but you're probably going to be using the pumping lemma, and so that's one of the reasons why we have the pumping lemma around, right? You'll notice there's no pumping lemma for Turing machines yet, so we're going to be in big trouble. So here's how we do this. Here is a DFA. Ta-da, there it is. It's JSON. Why not? What else would it be? Oh, that's kind of goofy. It's a tuple of JSON? I think that's still JSON. I'm not sure. We've got our states. We've got our alphabet, 0, 1. We've got our delta. My delta is not a function, right? But it's a specification of a graph, right? I can still apply it like a function. We've got our start state and we've got our accept state, right? So what are we going to do here? Well, we can sort of tease this a little bit already and say, well, we're going to come in with Q1, and we're going to notice that Q1 can get to Q2, and also back to Q1. And we're going to notice that Q2 can get to Q1 and also to Q3, and we're going to notice that Q3 is the thing we're trying to get to, right? Where's F? Oh, there it is. So yeah, there's a path through there. We go Q1, Q2, Q3. And you say, what letters? And I say, why would I care what letters? I'm just deciding if this thing's empty or not. I'm not telling you what's in it. So how are we going to do this? We're going to express a DFA to a Turing machine. I'm going to use strings for straights and ints for letters. Why not? I could use anything for anything, right? That doesn't matter. That's just a matter of encoding. So this is D of E DFA. We're going to take Q, which is a set of states, S, which is a set of symbols, D, which is a dictionary, and it's a little more complicated than a dictionary. It's a dictionary of dictionaries of string ints, right? Q0 is a state, and F is a state. Okay. We're going to set the current state to be Q0. Now, to be a little bit confusing, we named Q0 the initial state here. That refers to the state we called Q1. So that's this Q1, which is this Q1, which is just the string. Okay, so I'm going to set the current state to Q0. Why is that? Well, because I'm going to do breadth first search from that state. And we're doing breadth first search because Professor Sipser wanted to. I wanted to take a transitive closure. He wouldn't let me, right? I'm doing this for you. Okay. I want to do everything with functions. Okay, then we're going to create a set of visited states. Have you done like Dijkstra's algorithm or something like that? Yeah, this is getting very close to Dijkstra's algorithm, right? We're going to see the shortest path to the accepting state, right? Okay. We've got to keep those states in order, so I'm going to specify this is a sequence, that is not a set. And why is that? Well, it's basically a stack. We're going to keep popping things out. There's a lot of noise going on out there. What do you think's going on? All right. We have to keep these in order because we're going to loop over all of them. And what's going to happen is if we get to the end of our list before we find the accepting state, well, that actually means we don't accept, right? So what are we going to do? We're going to do visited, and we're going to find the current transitions. What are the current transitions? Well, we're going to look in delta, which we were provided, right? We're going to look in delta, and we're going to see all of the transitions from delta to other states. These are the outgoing edges of the current state. That should probably be Q0, I'm assuming. I don't know that I ever got this code to run. So we're going to say for each transition in the set of transitions, what are we going to do? We're going to do something. What are we going to do? Well, let's look back at this real quick. And what I wanted to do is I wanted to specify how we're going to be able to write Python loops here. The important thing to me is if I loop over a dictionary, I loop over the keys, not the values. And we showed this yesterday. I don't know if you remember. It's not a big deal. But let's look at one example. I'm going to create a dictionary. It's going to say 1 maps to A, 2 maps to B. And all I'm going to do is say print key for key in B. And so I'm going to see 1 and 2. So I'm getting these things, the keys of my key value pairs. Are you familiar with the term key value pair? Does that work for you? A dictionary has keys that correspond to values.
Yes, I know.
Yeah. Is there something else you'd call this other than a key?
No, just key and value, that's it.
Yeah. So anyways, we're seeing the keys. It's the first value of the ordered pair, whatever you want, right? So when I loop over DQ1, this is DQ1. So if I print all that stuff out, I'm going to get 0 and 1. That's not super helpful to me because I'm trying to get the states. So what am I going to do? I'm actually going to look at the symbol in the transitions. The symbols are the things I read on the tape. I don't care at all what the symbols are, but I'm going to look up what each transition is for the symbol. So I'm going to look up the state I go to from each symbol for the symbol in transitions, and that's going to be the state. And then I am going to append the state to the end of visited, right? This is a little bit cursed because we actually don't want to be appending this if state is already in there. So, okay. So what we actually need to do is we need to put this whole thing in a loop. And let me go back here. So this is for symbol in transitions, state equals transition symbol, visit dot append state. So I'm going to look at Q0. I'm going to look at all the transitions out of Q0. I'm going to take everything which has a transition out of Q0, and I'm going to append all of those states to the places that I visited. Same as Dijkstra's algorithm, right? Now I'm going to loop that. I'm going to count which states I've examined. Well, the count is less than the visited count. I'm going to look up visited count. What is that? That is the count number of the visited list, which I am populating here. Then for each symbol in the transitions, I'm going to look up the new state that I get to from that symbol, and I'm going to add that to the list of states. Are we allowed to use length? Of course we are, because I can just write down the number length somewhere else. So even if I can't calculate the length of a list, I can write it down somewhere. Are for and while cheating? Of course not. I have closure under star, so I know I can write loops. Right? I added here if state not in visited. That's getting a little sketchy. Now you're telling the Turing machine to read the entire list and see if something's in the list before adding it to it. I don't know. But perhaps you can say, for these two things, check to see if they're the same symbol. Do that for the whole list or something like that. Right? So I would probably not write not in a Turing machine. I would probably write some loop where I check equality for all of them. To me, Python in is a little bit too powerful. This in is different because this is an in and a for loop, and that's just do this thing, then run yourself again. So that's just a loop back to the beginning of an earlier state. Okay. I expressed this. This is LaTeX I had to expose because I had no other clear way to do this. So that's how I expressed the LaTeX. But I just translated my Python into an English language description. I don't know what you're going to do in your life, but if you enter a doctoral program, it's my expectation that people in that doctoral program will expect you to write proofs like this. And my expectation is if you're dealing with engineers, they're going to expect you to write proofs like this. I don't care how you write your proofs, just make sure you know what you're doing, right? And if you know what you're doing, you can always translate back and forth. There's a lot of things that I end up writing something very, very close to proofs to that are not really the classical definition of a proof, but like, say I want to convince my colleagues that a double major is sufficiently rigorous, right? Well, what do? I do this with CS math, because I do both of them, right? I look up the national standards for a math degree, and I look up the national standards for a CS degree, and I demonstrate that 12 courses meet the standards for both, and then my colleagues accept that, and then we let students graduate on time, right? So this is something that is outside of the scope of programming, but I use the same techniques. It is if I could write a Python script that does it. Well, I can translate my Python script into an email, and I can translate my email into a Python script, right? This makes no difference to me. So this is the acceptance criteria. If state not in F, return true, blah, blah, blah. So all you do is you populate the list of all of the states that you can reach from the starting state. You check to see if it has any intersection with the acceptance state. If you do, you return true. Otherwise, you return false. Or you just don't return anything at all. You don't care if you return, right? We're writing a decider in this case, so we are supposed to return false. But if you're just trying to recognize it, you can just return anything. Okay. Let's copy F to another tape. Check it before checking the visit tracker. Whatever. Okay. This halts because there's finite states. We can only keep computing as long as we're adding new states. There's a finite number of states. This thing's a decider. Good for us. So this is theorem 12. And I think this is one of my first ones I have a Python proof for. But I liked expressing this as Python, and I hope you do as well. Theory 13, this is the equivalent criteria for the DFA. What is this? Given the specification of two DFAs, can we conclude that the languages are the same? Not that the DFAs are the same, but that they accept the same language. This one, I think, this was a little non-intuitive for me, right? So what are we going to do? No problem. I've demonstrated I can emulate these, and I can demonstrate I have more than one tracks. I run both of them on the two tracks next to each other. Then I take another DFA, and this DFA, what does it do? It accepts if only A or only B accepts. So this is a closure property we didn't prove. This is XOR, right? This is the intersection, right? And so we're going to say, all right, here's a Turing machine A, or no, here's a DFA A, here's a DFA B. Run both of these in parallel and accept if one of them accepts, but not both. So what does this mean? This is the same thing as our union thing, which we take over the accepting states. But what we say is, you must be in an accepting state in one of them and not be in the accepting state in the other one. So the cross product is not F, the acceptance state, cross Q, all of these states. It is F1 cross Q2 set minus F2. Union Q1 set minus F1. So it's this sort of complicated series of states you have to be in. It's not that bad. You could probably write it out if you wanted to. It's very, very tedious to write XOR, right? But what we demonstrated is we can write a DFA that does this now. And then what do? Oh, we can check to see if DFAs are empty or not. So we just use the eDFA we just wrote. We see if the intersection, or what is it? It's like the set exclusion. It's the disjoint union. Some sort of complicated Venn diagram plot, right? We see if that thing's empty, and if it is, then they're equal. Can we also write an equality checker for regular expressions? Understanding check. Can I do this? I'm going to do my dramatic reveal now. I don't want to torment you with this too long. They're just DFAs. They're logically equivalent. So you convert the regular expressions into a DFA. Sorry. The regular expressions are equivalent to a DFA, so you just convert them into DFAs and then run the DFA prover. And this is one of the reasons we go back and forth between all these times. It's like, ooh, can I show that this DFA is equivalent to a regular expression? Of course you can. We just turn the regular expression into the DFA, then we see if the DFAs and the regular expressions are equivalent. And throw our hands up. And that's all we have to do. That's the end of the day. My voice is dead. That's why we're ending now. Let's do a little bit of trip planning. So I'm assuming you're going to be responsible for